Tin was employed in the 16th century for tinning iron, and although zinc and bismuth were often confused with antimony, yet a better knowledge of them was acquired, and the tutty from zinc ores was employed for making brass. One of the earliest treatises on glass manufacture is that by Antonio Neri, entitled L'arte veterae distinta in libri sette, ne quali se scorpono maravigliosi effetti e s'insegnano segreti bellissimi del vetro nel vuoco ed altre cose curiose, which was published in Florence in 1612, and in Latin at Amsterdam in 1681. In this work, Neri details his extensive experience, and it contributed to the diffusion of a knowledge of special ceramic operations. In the 16th century are found the first dependable observations on the manufacture of ruby glass by means of gold, and considerable skill was obtained about 1600 in the production of artificial gems. Johann Baptista Porta, 1538 through 1615, of Naples, was the author of a treatise, De Germarum Adulteris, in which recipes for preparing imitation precious stones were detailed. Agricola, in his treatise De Re Metallica, gives the first drawing of the interior construction of a glass furnace, and in this work, as well as in Mathesius, Sarepta, or Bergpostel, 1654, are found explicit and interesting directions about the manufacture of glass, as carried out in Venice, Germany, and Bohemia. In Bohemia, the glass industry began to flourish in the 16th century, the purity of the materials occurring there enabling glass manufacturers to produce the colorless glass for which the Bohemian glasshouses have long been famous. When the Venetian glass manufacture fell into decay, Bohemian glass replaced Venetian. The first manufacture of glass in England is that of window glass, established in the 15th century, but the product was not satisfactory, and in the reign of Elizabeth, French artists were brought to London, and these carried on their trade of making window glass at Crutched Friars in 1557, while flint glass was first manufactured at a glasshouse at Savoy House in the Strand. Mirror glass was manufactured at Lambeth by Venetian workmen brought over by the Duke of Buckingham in 1670. Glass works were established in France at an early date, but it was not until the 18th century, when workmen were brought from Germany, that a pure type of French glassware was produced. One of the important discoveries of this period was that of cobalt blue by Schurer, a Saxon glassblower who obtained it on fusing the cobalteous residue from the manufacture of bismuth with glass. This latter became known as Zaffirin smalt. The efforts of Palissy in extending the knowledge of ceramics have been referred to, and it only remains to state that Johannes Porta was engaged in similar work in Italy about the same time. These savants devoted themselves with self-sacrificing assiduity to the production of glazed and colored faience, and laid the foundation of modern art pottery. In dyeing, a variety of vegetable colors were employed. Indigo and cochineal were imported from America and the West Indies, and numerous observations were made on dyeing processes. Drebel learned that a solution of tin in aqua regia could be employed for fixing colors on cloth about 1630, and the methods of mordanting with alum and iron solutions were improved. The art of printing proved for dyeing, as well as for other arts, its great pioneer and propagator. In the middle of the 16th century, Plictho's Art of Dyeing was published. This treatise gave general instructions for dyeing all kinds of fabrics, and laid the foundation for that improvement of this art which soon after followed throughout Germany, France, and England. It is interesting to note that the use of indigo was forbidden by the English Parliament in the reign of Queen Elizabeth, and that this act remained in full force till the time of Charles II. Considerable interest was evinced in the distillation of liquors during this period, and numerous works upon this subject appeared. Among these were the following: Hieronymus Saler's Liber de Arte Distillandi de Composistis, 1500, 1512, and 1527. John French's The Art of Distillation, 1651, and L. Schultz's Distillatoria Curiosa sui ratio ducendi liquores coloratos per alembicuum, 1674. Many improvements were made both in distilling apparatus and in the methods of distillation, and the distillation of brandy became an industry. The word distillation, up to the end of the 14th century, meant the separation of the more light or subtle parts of anything from the more heavy or gross by a process of dropping. Thus Geber and others included the filtration of a liquid as a variety of distillation. The Latin word distillo applies to a dropping liquid, but such employment of the term does not appear after the 14th century in chemical works, although the older use of distill is still found in ordinary writings, especially in poetry, and occurs in Fielding and Shakespeare. The process of distillation was classified in various ways. For instance, according to the source and mode of application of the heat, the shape of the alembic or distillatory vessel, and the direction impressed on the vapor upward or downward, distillatio ascensum vel descensum. The heat was applied in the form of the direct heat of a fire, or the heat conveyed through water or through sand, or the direct heat of the sun. Porta, about 1585, employed concave mirrors to concentrate the sun's rays. Fairly, repeated distillation was often prescribed, as the purity of the distillate was thought to be increased each distillation up to the 5th distillate, which was termed the quintessence. An alcoholic distillate obtained in this way from selected wine was considered to possess great medicinal value. During the 16th and 17th centuries, the distillation of fermented alcoholic liquids became subject to state supervision in many European countries. In Ireland, where it has been shown that the distillation of a spirit from fermented barley was practiced in 1170, up to 1556, the distillation of spirits was carried on without license or taxation. In the reign of Henry VIII, distilleries were established in Pembroke by Irish settlers, and it is considered likely that the soldiers of Henry II, 300 years previous, brought back with them the knowledge of whiskey, or uisc bietha. The manufacture of aqua vitae from malt appears to have been common in Scotland and England in 1494, and in the middle of the 17th century, the manufacture of spirits was made a source of revenue by excise duties on the amount manufactured. In the Tudor and Stuart period, licenses had been required to use stills. The knowledge of chemical compounds, especially in the preparation of inorganic compounds, showed decided improvements, and the beginning of qualitative analysis are sought for in this period, insofar that conclusions concerning the presence of one or another constituent were deduced from the appearance and behavior of precipitates and of salts, which crystallized out from solutions. Glauber designed several forms of furnaces and casting vessels, which were found to be useful in the preparation and investigation of a number of inorganic substances. As a result of the attention paid to the products of vegetable and animal assimilation, organic compounds became known in rapidly increasing numbers, but the composition of these bodies remained quite undiscernible. It is worthy of note that many of the iatrochemists assumed that oil or fat contains a hidden acid, basing their conclusion on the old observation that fats were acted upon and changed by alkalis. The importation of sugar from Spain, Portugal, Madeira, the West Indian Islands, and Brazil soon made this article better known throughout Europe. Libavius, in his Alchemia, 1595, mentions Saccharine crystallini quod candi appellant, and he recommends a plan of purifying Madeira sugar by means of albumen, and Angelus Sala, in his Saccharologia, advises the use of egg albumen and lime water for this purpose. Milk sugar, occurring in the milk of mammalia, especially in that of the herbivora, was first examined by Fabrizio Bartoletti in 1619. It was termed by him as manna S nitrium surrelactis. It was more closely examined by Testi in 1698. Glauber noticed in 1660 that a granular sugar is contained in honey, raisins, and in the juice of sweet cherries, but he did not point out that it differs from cane sugar. End of section 6.
Section 7 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The Science History of the Universe, Volume 4. Edited by France Rolt Wheeler. Chemistry. Chapter 6. The Early Phlogistic Period. Heretofore, the inducements to a study of chemical phenomena had been successively a belief in the possibility of transmutation and a conviction in the potency of heroic medicines prepared in the chemical laboratory. But from the middle of the 17th century onward, another aim is manifest in the works of the masters. For from the time of Boyle forward, the great end of chemistry was recognized as being the discovery of new chemical facts, with the object of arriving at the truth alone, and thanks to the spirit of true investigation, which had begun to extend itself to chemistry, and the effect of the inductive method of Francis Bacon, chemistry assumed its proper place as a science. As an approach is made to modern times, it becomes more difficult to define historically the successive phases of chemistry. The learned societies which were founded in the second half of the 17th and the beginning of the 18th centuries, and whose periodicals furnished ever-accumulating data for the discussion of old and the initiation of new theories, and disseminated the results of chemical investigations in general, assisted materially toward the healthy progress of chemical science. But nevertheless, firm obsequiousness to any one school of scientific thought was not to be expected, nor was it found. The London Royal Society was founded by Charles II, and was incorporated by him in 1662, under a royal charter, for the improvement of natural knowledge. The first volume of the Philosophical Transactions of that society bears the date 1665, and ever since its foundation, the Royal Society has been a nucleus around which has clustered the scientific genius of Great Britain. In 1666, the Académie Royale was instituted in Paris under the protection of Louis XVI, and its memoirs began to appear in 1699. Other scientific societies, the Accademia del Cimento of Florence, 1657, the Academia Naturae Curiosum of Vienna, 1652, and the Berlin Academy, 1700, also brought together those who were in sympathy through their devotion to knowledge, and by the interchange of their ideas, thought was quickened and the advance of science aided. The reciprocal action of chemistry and allied branches of science upon each other was also promoted by bringing together their respective exponents, and the discussion of scientific researches helped more thoroughly to sift the evidence on which their conclusions were based, and tended to promote increased accuracy and simplicity of thought and expression. Although the literature of the day bears record of many observations, isolated discoveries, and discussions on chemical problems, yet there was one problem which engrossed the attention of almost all philosophers during the 17th and 18th centuries, and this was the explanation of fire and the phenomena caused by fire. Notwithstanding the fact that here scarcely any two chemists were agreed in their conclusions, their modes of arriving at them showed remarkable similarity. Little note was taken of the proportions by weight in which substances entered into reaction. The qualitative side of phenomena alone was being considered. This period of about 120 years, from Boyle to Lavoisier, may therefore be described as that of qualitative chemistry, a step toward the quantitative work of the modern period, and an immense step forward from the speculative and fortuitous chemistry of the preceding periods. It was a period of generalization, for just as fire was to be explained by the assumption of one general principle, phlogiston, a doctrine which influenced chemists to such an extent that this period is characterized as the phlogistic period. So the general properties of acidity and causticity were to be viewed as conferred by one fundamental acid and one fundamental alkali respectively. And although it was itself handicapped by erroneous views, the phlogistic period contributed largely to the refutation of alchemical and iatrochemical errors, and was a highly productive period for chemistry. Robert Boyle, 1627 to 1691, was the seventh son and 14th child of Richard, Earl of Cork. He was born at Lismore in Munster. At 8 years of age he was sent to Eton, where, says he, a perusal of Quintus Curtius conjured up in me that unsatisfied appetite for knowledge, that is yet as greedy as when it was first raised. After about 4 years at Eton, Boyle went to his father's seat in Dorset, and afterward travelled. He became a student at Geneva, and continued his studies at the manor of Stallbridge from 1644 to 1654, when he settled at Oxford. In 1668, Boyle moved to London, and was a prominent member of the then newly constituted Royal Society. He was elected president in 1680, but refused to serve, owing to a scruple he entertained as to taking oaths. In 1689, his health began to fail, and he issued an advertisement restricting the visits of his acquaintances. He also had a board put up outside his house, announcing when he received visits. Boyle's health had never been good. From the age of 21, he suffered from stone, and much feared that if it forced him to take to his bed, the pain of it would become intolerable. He died, however, without pain, and almost without serious illness. Boyle developed talent early, and at 21 he had already written on ethics, and published several moral and religious essays. In 1665, he published his Occasional Reflection upon Several Subjects, which procured him the satire of Swift in a pious meditation upon broomstick, in the style of the Honorable Mr. Boyle. It would be needless to attempt to go over the whole ground of Boyle's work, although there is much in it of interest, even at the present time, as, for example, his papers on the saltness of the sea and the nature of the sea's bottom, and his essay on the intestine motions of the particles of quiescent solids, wherein the absolute rest of bodies is called in question. He was perhaps the first to draw attention to the desirability of studying the forms of crystals, and his papers on the figures of salts contains many curious observations. In his experiments about the superficial figures of fluids, especially of liquors contiguous to other liquors, he breaks ground which has taxed the energies of our greatest mathematicians. His treatise on cold abounds with striking and original experiments. For example, he demonstrates the expansive power of freezing water by bursting a gun barrel filled with water and securely plugged, by placing it in a mixture of snow and salt, a freezing mixture which he himself introduced in England. His essays on the usefulness of experimental natural philosophy were of the greatest service in his time in furthering the cause of science, by showing how the material interests of civilization may be prompted by its study, and lastly, his tract on unsucceeding experiments must have been, to quote Thorpe, as the wine of gladness and the oil of consolation to many a despondent virtuoso. Boyle was born in the year in which Bacon died, and Boyle's place in the history of science is that of the first true exponent of the Baconian period. and The Skeptical Chemist is his greatest work. This work probably contains a greater number of well-authenticated facts than is to be found in any other chemical treatise of its day. But the real merit of this work consists in its determined attack on the authority of the Peripatetics and the Paracelsians. To quote from his own statement in The Skeptical Chemist, "To acquaint you with the divers of the conjectures, for I must yet call them no more, I had concerning the principles of things purely corporeal. For though, because I seem not satisfied with the vulgar doctrines, either of the Peripatetic or the Paracelsian schools, many of those that know me have thought me wedded to the Epicurean hypothesis, as others have mistaken me for a Helmontian. I should tell you that I have sometimes thought it not unfit, that to the principles which may be assigned to things, as the world is now constituted, we should, if we consider the great mass of matter, as it was whilst the universe was in making, add another, which may conveniently enough be called architectonic principle or power, by which I mean those various determinations and that skillful guidance of the motions of the small parts of the universal matter, by the most wise author of things, which were necessary at the beginning, to turn that confused chaos into this orderly and beautiful world. For I confess I cannot well conceive how from matter, barely put into motion, and then left to itself, there could emerge such curious fabrics as the bodies of men and perfect animals, and such yet more admirably contrived parcels of matter as the seeds of living creatures." Boyle is severe upon the affected mysticism of the Spagirists. They may be as obscure as they like about their elixir and the rest of their grand arcana, yet when they pretend to teach the general principles of natural philosophers, this equivocal way of writing is not to be endured. For in such speculative inquiries, where the naked knowledge of the truth is the thing principally aimed at, what he does teach me worth thanks, that does not, if he can, make his notion intelligible to me, but by mystical terms and ambiguous phrases darkens what he should clear up, and makes me add the trouble of guessing at the sense of what he equivocally expresses, to that of learning the truth of what he seems to deliver. Indeed, Boyle does not hesitate to say that the reason why the Spagirists wrote so obscurely of the three great principles was, according to Thorpe, that not having clear and distinct notions of them themselves, they could not write otherwise than confusedly of what they had confusedly apprehended. They could scarcely keep themselves from being confuted, but by keeping themselves from being clearly understood. Home thrusts which must have made many a Helmontian wince. The effect of such hard hitting is made evident on the most superficial comparison of the general style of chemical treatises, immediately preceding Boyle's time, with those published toward the close of the 17th century. The skeptical chemist compelled the decline of the doctrine of tria prima, and before the close of the century, the Paracelsians were as much out of date as a phlogiston would be today. Boyle indeed appeared to incline to the belief that all matter is compounded of one primordial substance. In other words, that all matters are merely modifications of the materia prima. To quote again from his Skeptical Chemist, "I consider that if it be as true as it is probable that compounded bodies differ from one another, but in the various textures resulting from the bigness, shape, motion, and contrivance of their small parts, it will not be irrational to conceive that one and the same parcel of the universal matter may, by various alterations and contextures, be brought to deserve the name, sometimes of a sulphureous, and sometimes of a terrene or aqueous body." How closely he was in accord with the modern spirit is shown in this remarkable passage. I am apt to think that men will never be able to explain the phenomena of nature, while they endeavor to deduce them only from the presence and proportions of such or such material ingredients, and considers such ingredients or elements as bodies in a state of rest, whereas indeed the greatest part of the affections of matter, and consequently of the phenomena of nature, seem to depend upon the motion and contrivance of the small parts of bodies. It was possible for Boyle to expose the shortcomings and fallacies of the then prevalent idea of element or principle. I mean by elements, as those chemists that speak plainest do by their principles, certain primitive and simple or perfectly unmingled bodies, which, not being made of any other bodies or of one another, are the ingredients of which all those called perfectly mixed bodies are immediately compounded, and into which they are ultimately reserved. I need not be so absurd as to deny that there are such bodies as earth and water, and quicksilver and sulfur. But I look upon the earth and water as component parts of the universe, or rather of the terrestrial globe, not of all mixed bodies. This conception of an element gave the term a positive meaning. Boyle also looked forward to the discovery of a much greater number of elements than was at that time assumed, at the same time maintaining that many of the substances then held to be elementary were not really so. Boyle was the first to state clearly that a chemical compound results from the combination of two constituents, and that it has properties entirely different from those of either of its constituents alone. He was, therefore, enabled to draw a sharp distinction between mixtures and chemical compounds, and to grasp clearly the main problem of chemistry, the investigation of the composition of substances. In doing this, he had the solid ground of experience and experiment under his feet, and could always bring forward evidence for the probability of his views. His endeavors to get at the root of the composition of bodies gave an impetus to the analytical chemistry, which before his time could hardly be said to exist. And we are at the same time indebted to him for fixing the meaning of a chemical reaction. Boyle appears to have been the first to employ the term analysis, in the sense in which it has since been used by chemists. Also, he devoted much attention to the inquiry of the cause of combustion and other similar phenomena, and although his attempts at explaining these were not very successful, his experiments on the role played by air in combustion aided the later solution of the problem. His investigations on air and gases led him in 1660 to the well-known discovery of the law that the volume of a gas varies with the pressure. Marriott educed this independently in 1677. Boyle's writings, which were extensively read in his own time, are characterized by simplicity of style and clearness of expression. They offer, as von Meyer observes, an agreeable contrast to the works of many in the other chemists of his time, who sought to hide their deficiencies in clear thought and accurate knowledge by metaphorical and mysterious language. In addition to other papers published in the Philosophical Transactions, the following works of his, which were brought out both in English and Latin, are to be particularly mentioned. The Skeptical Chemist, Chemistus Skepticus, first published anonymously in 1661, and afterward in many editions with Boyle's name as author. Tentamina Quidam Physiologica, 1661, and Experimenta et Considerations de Coloribus, 1663. Editions of his complete works were published in London in 1700, 1725, and 1744. A contemporary of Boyle who made important observations on combustion was Robert Hooke, 1635 to 1702. Hooke was born in the Isle of Wight, and was originally intended for the church, but he was of a weakly constitution, and much subject to headache, and owing to these causes the idea was finally abandoned. His leanings were first shown in a considerable aptitude, as a boy, for constructing mechanical toys. After his father's death, Dr. Busby took him into his house and supported him at Westminster School. After leaving school, he went to Christ Church, Oxford, and in 1655 he was introduced to the Philosophical Society. Here his talents were speedily discovered, and he was employed to assist first Dr. Willis and then Mr. Boyle. In 1662, he was made curator of experiments to the Royal Society, and when this body was established by charter, he was one of the first nominated to fellowship. He obtained several professional posts, and in 1665 he published in folio his Micrographia, or some physiological descriptions of minute bodies made by magnifying glasses, with observations and inquiries thereupon. It was dedicated to Charles II. It is usual to state that Hooke anticipated the modern view of the nature of combustion in this treatise, but it will appear from the following extract that whatever value may be assigned to his work, it cannot be claimed that he did more than recognize the part played by the air in the process, while still adhering to the conception of a sulphureous principle, which is lost by the body during combustion. Thus he observes, "From the experiment of charring of coals, we may learn that the air in which we live, move, and breathe, and which encompasses very many, and cherishes most bodies it encompasses, that this air is the menstruum, or universal dissolvent, of all sulphureous bodies, that the dissolution of sulphureous bodies is made by a substance inherent, and mixed with the air, that is like, if not the very same, with that which is fixed in saltpetre, which by multitudes of experiments that may be made with saltpetre will, I think, most evidently be demonstrated. The dissolving parts of the air are but few. That is, it seems of the nature of those saline menstruums, or spirits, that have very much phlegm mixed with the spirits, and therefore a small parcel of it is quickly gutted, and will dissolve no more. Whereas saltpetre is a menstruum, when melted and red hot, that abounds more with those dissolvent particles, and therefore, as a small quantity of it will dissolve a great sulphureous body, so will the dissolution be very quick and violent. It is observable that, as in other solutions, if a copious and quick supply of fresh menstruum, though but weak, be poured on or applied to the dissoluble body, it quickly consumes it. So this menstruum of air, if by bellows or any other such contrivance, it be copiously applied to the shining body, is found to dissolve it as soon and as violently as the more strong menstruum of melted nitre. The completion of Hooke's theory was effected by John Mayow, who was born in the parish of St. Dunstan, London, in 1645. In 1674, he produced the treatise on which his fame rests. It is entitled Tractatus Quinque Medico Physici Quorum Primus Agit de Sol Nitro et Spiritu Nitro Aereo Secundus de Respiration Tertius de Respiration Fetus in Utero et Ovo Cordis de Motu Musculare et Spiritibus Animalis Ultimus de Rachitidae Studio Joe Mayo LLD in Medici Nec non col omne amen et University Oxon Soci Exoni e Theoro Sheldoniano andom. Mayow's assumption that atmospheric air contained a substance, the spiritus nitro aeris, also present in saltpetre, which combined with metals when they were calcined, and which sustained respiration and convertus venous blood into arterial, was bound to result in the right interpretation of the phenomena of combustion, when the observations which had led to it were sufficiently extended. Mayow's early death in 1679 was perhaps the reason why this did not occur, the development of the new chemistry being greatly retarded as a result. Two members of the French Academy became prominent at this period, Lemery and Olmberg. Wilhelm Olmberg, 1652 to 1715, was a lawyer, but gave up the practice of his profession to study natural science and medicine. He knew both Boyle and Kunkel, and was a good observer and skillful in carrying out his experiments, but a poor interpreter of the results. He was trammeled by alchemistic views, maintained that substances consisted of mercury, sulfur, and salt, and took little part in establishing the new theories. He contributed a large number of papers on chemical, zoological, botanical, and physical subjects to the French Academy. Nicolas Lemery, 1645 to 1715, was especially renowned as a teacher, though he was also a good worker, dealing in the practical rather than the theoretical. His son, Ludwig Lemery, was also a distinguished chemist. The elder Lemery's greatest work was the writing of his textbook of chemistry, Cours de Chimie, 1675, which embraced all that was known of chemistry, and endeavored to give a suitable connection between the facts recorded and to systematize them. This was for many years the best textbook on the science, and was issued in 32 editions. 13 editions appeared during the author's lifetime, and a last much-changed one was issued by Baron in 1756. Two German contemporaries of Boyle were Johann Kunkel and Johann Joachim Becher. Kunkel was essentially an experimentalist. He was imbued with a belief in the philosopher's stone, and regarded mercury as the necessary component of a metal. He was born at Rendsburg in 1630, and died in 1702. He was the son of an alchemist, and himself passed much of his life as the employee of sundry German princes, among them the Elector John George of Saxony, the great Elector of Brandenburg, and the Dukes of Lauenburg, in the unsuccessful pursuit of the philosopher's stone. Before the second half of the 17th century, the blowpipe had been used neither in chemical analysis nor for working glass. It was Kunkel's task to demonstrate the case in which a metallic calyx might be reduced by heating it on charcoal before the blowpipe, and to institute a more expeditious mode of hermetic sealing than that of inserting the drawn-out neck of flask or other vessel in a hot fire, hitherto in vogue. Kunkel was the first to recognize an analogy between putrefaction and fermentation, and to show how the production of vinegar in the latter process depended on the initial formation of alcohol and avoidance of low temperature or presence of acids. Among his treatises, the following may be mentioned: Offenlich Zuschrift von Phosphoro Millibri Inducen Ductenten Wunderpilulien, 1678. Ars Vitraria Experimentalis, 1689, and Philosophia Chemica Experimentis Confirmata, 1694. Johann Joachim Becher, who was born at Speyer in 1635 and died in London in 1682, worked almost contemporaneously with Kunkel, although more for the theoretical explanation of already observed facts than for the practical side of the subject. But in his unsettled life and his inclination toward new schemes, he resembled the latter. He worked as an alchemist at the courts in Mainz, Munich, and Vienna, but he was too honorable to deceive his patrons, and entirely too candid to allow of his remaining long in any one place. In theoretical questions as to the composition of substances, Becher attempted to revive the old ideas of Paracelsus in another form. In place of mercury, sulfur, and salt, he adopted 3 earths, of which all inorganic, subterrestrial bodies should consist, vis-a-vis the mercurial, the vitreous, and the combustible, terra pinguis. The nature of any material depended on the proportions in which these 3 fundamental earths were contained in it. Of especial importance was Becher's assumption that when substances were burnt or metals calcined, that terra pinguis escaped. fire dissolves and breaks up all things made of different parts. In metals, the more volatile part is expelled. That is, he regarded combustion as a destruction. Hence, he concluded that every combustible substance must in itself contain the cause of combustibility, and that a substance incapable of being resolved into others, an element, cannot burn. It was from this conception that Stahl's phlogiston theory originated. These theoretical views are to be found in Becker's first work, Physica Subterranea, 1669, and in his last, Thesis Chemicae, 1682. His doctrines acquired great celebrity through Stahl, whose work belongs for the most part to the 18th century, on which he conferred a character of its own by his development of the phlogiston theory. End of section 7. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com.
Section 8 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Sandra Kinzer, Madison, Wisconsin. The Science History of the Universe, Volume 4. Edited by Francis Rolt Wheeler. Chemistry, Chapter 7. The Phlogistic Period Proper, Part 1. One of the most interesting chapters in the history of chemical science is that dealing with the study of the phenomena of combustion and their interpretations. As Freund observes, it lends itself specially well to the purpose of indicating within the scope of not too complicated phenomena how a theory arises, how it is applied, how the conservatism inherent in the human mind is reluctant to give up an accustomed interpretation of nature, even when it no longer answers to the first requirements of a theory. That is, when it no longer explains the facts and laws observed in the class of phenomena to which it refers, but how, after all, facts are and always must be strongest, and hence how a theory is finally given up when no longer able to deal with the facts, and how its place is then taken by another better fitted to do so. The effect of heat on matter had from early times been a subject for observation and experiment, which soon led to classification and generalization. It was observed that while some substances are not permanently changed when heated, sand, noble metals, etc., others are, wood, sulfur, base metals, etc. The burning of substances, that is, the occurrence of a permanent change marked by the appearance of flame, great evolution of light and heat, and the remaining behind of ash, naturally arrested attention and the view that substances were combustible in virtue of the common presence in them of fire matter goes back to the time of the Greek philosophers. That the substances left behind when wood is burnt or when metals such as copper and lead are heated were alike called cineres, ashes, bears witness to the fact that even then these two phenomena, outwardly not very similar, the burning of wood and the change produced by heating metals, were already classed together. The name of calces, Latin calx equals lime, for burnt metals, which up to about 1600 was used along with cineres, and after that exclusively, is due to the Arabian alchemists, and suggests an analogy with the burning of chalk, the burnt metal being produced from the metal by the same process as quicklime from chalk, namely by heating. All through the Middle Ages, the idea was retained that what occurs when substances burn with flame and when metals are changed to calces is of essentially the same nature and must therefore be explained by the same cause. For many centuries, sulfur was looked upon as the principle of combustibility, and metals which could be burnt, that is, calcined, owed this to the common presence in them of sulfur. Ubi ignis et calor ibi sulfur summed up this view. Becher's Terra Pinguis had much in common with the fire of the schoolmen and the sulfur of Albertus Magnus and Paracelsus. The scope of the phenomena to which this explanation of combustion applied was extended by Stahl, and the theory of the phenomena of combustion and other analogous processes, which were to be explained by the assumption of the hypothetical phlogiston, was the point round which chemists in general gravitated during the 18th century. Until the appearance of Lavoisier, the phlogiston theory received the assent of most investigators. George Ernst Stahl, born at Ansbach in 1660, devoted himself to the study of medicine and acquired, first at Jena and later on at Halle, to which university he had been called as professor of medicine and chemistry in 1693, the reputation of a distinguished physician and academic teacher. When he was appointed physician to the king in 1716, he removed to Berlin, where he successfully strove for the extension of chemical knowledge until his death in 1734. He investigated chemical problems in the true scientific spirit, himself guided by the ardent desire to discover the truth. He was able to draw around him pupils animated by a similar purpose. The most eminent among the Berlin chemists of the succeeding generation studied under him. Even in his own lifetime, the doctrines which he taught, together with a number of valuable detached observations, were widely disseminated by means of his writings, and especially by his lectures, the latter of which were published by several of his pupils. Stahl, however, exercised his greatest influence both upon his contemporaries and upon the succeeding generation by his phlogiston theory, which eclipsed all his other chemical work. Phlogiston was defined by Stahl as materia aut principium ignis, non ipse ignis, and was conceived to be a very subtle matter, capable of penetrating the most dense substances. It neither burns, nor glows, nor is visible. It is agitated by an igneous motion, igneo motu, and it is capable of communicating its motion to material particles apt to receive it. The particles, when endued with this rapid motion, constitute visible fire. The igneous motion is gyratorius su vorticillaris. Heat is an intestine motion of the particles of matter. Phlogiston was a new name for an old principle. We know that the idea of the existence of a subtle fire innate in matter has pervaded physical philosophy from the earliest times. Phlogiston was, as Rodwell notes, another name for the pure fire of Zoroaster, the atechnikon pyr of Zeno, the subtilis ignis of Lucretius, the elemental fire, astral fire, sulfur, or sulphureous principle of the chemists, the calor caelestis of Cardanus, the sideric sulfur of Paracelsus, the materia caelestis of Descartes, and the terra inflammabilis of Bécher. The functions of this entity had been varied by different thinkers, almost as much as its name, until Descartes gave them accurate definition. The theory of phlogiston was the theory of the materia caelestis extended in a chemical direction. Phlogistic chemistry was Cartesian chemistry. Descartes defined the physical functions of the materia caelestis, while Bécher and Stahl defined its chemical functions and applied them to the explanation of diverse chemical phenomena. Throughout the writings of Bécher and Stahl, we find a sprinkling of Cartesianism. They did not, however, adopt the system in its entirety, but appear to have discarded the second and third elements, and adopted the first as the parent of their own system. The theory of phlogiston was essentially and completely a syncretistic theory. It was built up, as Rodwell observes, of idola theatri, collected from various sources, and these were cemented together by the particular idola specos of Bécher and Stahl. In this process of syncretism, the merit of these men lay. Their fault was a too hasty generalization. In that stage of chemistry, syncretism was inevitable. Indeed, all theories are more or less tinctured by it, with the exception of those which emanate from a new mode of experimenting, such, for example, as Kirchhoff's theory of the constitution of the sun. A theory proceeds by slow evolution until it dominates or is destroyed, and it was thus with the theory of phlogiston. Arising under the most favorable conditions, it attained full development, became most cardinal, most sovereign, and then fell. For 28 years, it was looking a half-formed thing through the mists of chemistry. For 34 years, it was growing in strength and proclaiming its dynasty. For 54 years, it was dominant, and it was fully 10 years yielding up the ghost. Bécher and Stahl were the prophets of a new mode of chemical thought, essentially classificatory, systematic, and syncretistic. In their day, chemistry was at the commencement of a period of transition, and they bridged the gap which existed between empirical chemistry and modern chemistry. They did not collect the materials for the structure. They did not altogether construct it, but they designed it and helped in the work of building. Albeit a bad bridge and built upon shifting sands, yet it was a channel of escape from mystic science, and many passed over to take refuge on the other side. To Stahl, however, belongs the merit of grouping together the phenomena of oxidation and reduction, as we now term these, albeit by the aid of a false hypothesis. The addition of phlogiston is equivalent to reduction and its withdrawal or escape to oxidation. The analogy between respiration and the decomposition of animal matters on the one hand and combustion on the other did not escape Stahl, who likewise assigned the chief role in these processes to phlogiston. The value of his theory lay therefore in the interpretation which it afforded of a variety of processes from one common point of view. The simplicity of this explanation blinded both himself and the generation which followed him to such a degree that they left unnoticed all the glaring contradictions between many actual facts and the phlogistic doctrine. Notwithstanding this, however, the latter was not an obstacle to the development of chemistry, considering that chemists like Black, Cavendish, Marggraf, Scheele, Bergman, and Priestley, who so greatly extended the science by their wide-reaching discoveries, were phlogistonists in the full sense of the word. Stahl's two most famous contemporaries were Friedrich Hoffmann and Hermann Boerhaave. Hoffmann, born at Halle in 1660, after acquiring a thorough knowledge of medicine, mathematics, and the natural sciences, practiced first as a physician and then became professor of the science of medicine in Halle, where he ultimately died in 1742 after an interregnum spent in Berlin. His most important work was done in medicine and in pharmaceutical and analytical chemistry. He combated with success the iatrochemical doctrines of Sylvius and Tachenius, which still held their ground with many physicians, exposing their absurdities and showing to what nonsensical deductions such exaggerations led. Hoffmann's views on combustion were very similar to those of Stahl. With respect to the calcination of the metals and the reduction of their oxides, however, he expressed opinions which approximate to those held at the present day, believing, as he did, that metallic calces contained a sal acidum in addition to a metal, the former of which escaped when the calces were reduced. This assumption did away with the similarity between combustion and calcination. These phenomena became indeed rather opposed to one another thereby, and with this the special use of the phlogiston theory vanished. Hoffmann was a very voluminous author, and his collected works in 6 volumes and 5 supplements, entitled Opera Omnia Physicomedica, 1740 to 1760, show clearness of style and precision of expression. Gmelin, in his Geschichte der Chemie, enumerates 122 chemical treatises by Hoffmann. Hermann Boerhaave was born at Voorhout, near Leyden, in 1668, where he received his education and became professor of medicine and afterward of chemistry and botany. The 36 years of his residence there were the most brilliant in the history of this university. Looking at his chemical work alone, he is found distinguished in the main as a teacher and for his skill in interpreting chemical facts and the clearness of his theoretical views. He exposed the errors of the iatrochemists and recognized chemistry as a distinct science. He also showed the falsity of the views held by the alchemists. He spoke only of things tested and observed by himself, and spared neither pains nor time to have his observations correct. For instance, the alchemists maintained that mercury could be fixed in the form of a fire-proof metal, without the addition of any other substance. Boerhaave kept mercury at a somewhat raised temperature in an open vessel for 15 years without noting any change. So, too, when heated higher in a closed vessel for 6 months, no change could be discovered. This convinced him that the fixing of mercury was an impossibility. The alchemists said also that if mercury was repeatedly distilled, a more volatile essence with peculiar properties could be obtained. Boerhaave carried out this distillation 500 times without securing the essence, and so he tested other of their peculiar notions and prescribed methods without obtaining the results promised. And as the methods were still credited in some quarters, he did good service in disproving them, and won for himself the reputation of being a most excellent and painstaking worker. His lectures were published first in the surreptitious edition, Institutiones et Experimenta Chemiae, 1724, and afterward corrected by him under the title Elementa Chemiae, 1732. 11 editions and translations were published in Germany, France, and England. Boerhaave appears to have concurred in the phlogiston theory in many points. At least he expressed no opinions contrary to Stahl's fundamental views, although he did not agree in regarding the calces of the metals as the earthy elements of these latter. The influence of Stahl's doctrine manifested itself more immediately in Germany, where it received the almost unequivocal support of chemists, Berlin remaining the center point of this theory. Among the men who upheld and endeavored to propagate it, Marggraf was the most active. Caspar Neumann, born 1683, and Johann Theodor Eller, born 1689, contemporaries of Stahl, were also active adherents of the doctrine in Berlin. Both of them, as professors at the Medico-Chirurgical Institute, were in a high degree active in maintaining and disseminating a knowledge of chemistry. Their own observations were, however, of little importance. Neumann made the first accurate observation of the acid obtained from ants, and the views of Eller were chiefly upon subjects of medical physiology and are full of crude speculations. Stahl's pupil, Johann Heinrich Pott, born 1692, improved chemistry by many valuable observations, but he was unfortunate in his explanation of these. He regarded boracic acid, for instance, a substance which he had himself investigated carefully, as consisting of copper vitriol and borax. The results which he achieved were not, as von Meyer notes, at all commensurate with his untiring perseverance, which he showed, among other ways, in his endeavors to prepare porcelain. Although an adherent of the phlogistic doctrine, Pott did not bring forward anything new in its favor. With regard to the nature of phlogiston itself, he could only express the opinion that it was a variety of sulfur. A notable achievement associated with his name was a wide extension of the method of dry analysis. His Chemische Untersuchungen was published in Berlin in 3 parts in 1757. Neumann's pupil, Marggraf, was the last of the well-known German chemists of the phlogiston period. Andreas Sigismund Marggraf was born at Berlin in 1709 and proved a most able experimenter. Indeed, it is for his many isolated discoveries that he is remembered, rather than for any influence exerted on the general trend of chemical philosophy. One of the most lasting benefits owed to him is the introduction of the microscope as an aid in laboratory work. The occasion was noteworthy. A paper appeared in the Memoirs of the Berlin Academy for 1745, in which Marggraf stated that small crystals of sugar might be seen with the aid of a microscope upon the finely divided and desiccated roots of the carrot and beetroot. He further stated that this sugar could be extracted by lixiviation with hot alcohol, and added that mere compression of carrot or beet will yield a saccharine liquid, from which the sugar might readily be extracted. These observations remained unnoticed until the continental blockade of France in 1806 urged its people to find some substitute for their imported sugar. Of prime importance was Marggraf's observations on phosphoric acid, whose principal physical and chemical properties he accurately described. He obtained this acid by burning ordinary phosphorus in the air and dissolving the resulting fleur de phosphore in water, also by heating phosphorus with concentrated nitric acid. Marggraf's work on the composition of gypsum was remarkable. He had noticed that potassium sulfate on heating with charcoal emitted the pungent smell of burning sulfur, and as this also occurred when gypsum or heavy spar was substituted for the potassium salt, they too must be compounds of sulfuric acid. One should not forget his introduction of potassium ferrocyanide as a reagent for iron, nor his separation of microcosmic salt from urine. He remarked that it was this salt which contained the phosphorus. With great talent for observation, Marggraf united the gift of deducing what were generally sound conclusions from his work. In one point, however, Marggraf, like all phlogistonists, was not in a position to do this. Although he had himself proved that phosphorus increases in weight by conversion into phosphoric acid, he could not free himself from the idea that phlogiston escaped during the process of combustion. And he could never be brought to see that this conception was an erroneous one, although the anti-phlogistic doctrine was brought out several years before his death. Marggraf's papers are, as mentioned, almost all contained in the Memoirs of the Berlin Academy. Most of them were published from 1761 to 1767 in 2 volumes, under the title Chemische Schriften. A French edition appeared in 1762. In France, the principal exponents of chemistry during the 18th century, until the downfall of the phlogistic system, were Geoffroy, Duhamel du Monceau, Rouelle, and Peter Joseph Macquer. Stephen Francois Geoffroy, the elder, to distinguish him from his less celebrated younger brother Claude Joseph, whose work was chiefly pharmaceutico-chemical, was born in Paris in 1672 and helped for some time in his father's apothecary shop. He gave himself up, however, to chemical and medical studies, and labored with great success as professor of medicine in the Jardin des Plantes from the year 1712 until his death in 1731. Geoffroy became well known throughout the scientific world by his researches upon chemical affinity. His Table des Rapports, tables of affinity, in which the results of his most important observations are collected, exercised a great influence upon the doctrine of affinity. His theoretical views were less idoneous. For example, he looked upon the iron found in the ashes of plants as having been produced artificially during the process of ignition. Geoffroy's views on combustion were in principle those of Stahl, though he expressed himself in the nomenclature of the earlier period, yet there was much promise in his conviction that the different calces were radically different bodies. A real service was rendered by him by the energy with which he attacked alchemistic frauds, subjecting these, as he did, to critical examination in the memoir Des supercheries concernant la pierre philosophale, presented to the French Academy. Geoffroy's treatises were published partly in the Memoirs of the French Academy and partly in the Philosophical Transactions. His long-celebrated work Tractatus de Materia Medica shows that he regarded chemistry as a sister science and an invaluable aid to medicine. Henri-Louis Duhamel du Monceau, born 1700, died 1781, of the school of Lemery and Geoffroy, spent his life in Paris, where his versatility gained for him a high reputation. His sterling work was not by any means in pure chemistry alone, but also in physics, meteorology, physiology, botany, and particularly in chemistry, as applied to agriculture. Duhamel's great achievement was the differentiation of the two alkalis, soda and potash. The composition of ordinary salt had hitherto eluded research. Stahl, it is true, believed one constituent to be an alkali, and an alkali quite different from potash, if one might judge by differences in the crystalline form and solubilities of their respective salts. There was a vagueness about his work, however, and it had met with little recognition. Duhamel published a paper in 1736 on sea salt, which put the matter beyond question. In it, he first showed that the base of salt was not in earth, for the addition of potash caused no precipitation. Then, that its several salts all differed essentially from those of potash corresponding. He laid stress, too, on the fact that the further one moves from the sea, the less the quantity of the new base, and the greater the quantity of potash in the surrounding vegetation. Subsequently, while describing minutely the differences between the analogous salts of these bases, Duhamel mentioned the yellow and violet colorations which they respectively give to a colorless flame. While Duhamel worked mainly as an academician, Guillaume François Rouelle, born 1703, died 1770, was occupied in teaching at the Jardin des Plantes, and some of his pupils, particularly Lavoisier and Proust, attained the highest eminence. At the same time, he was also busy as an investigator, as many admirable observations and conclusions drawn from the latter's show. Rouelle fixed the meaning of the term salt in the Memoirs of the Academy for 1745 from a far more general point of view than von Helmont or Tachenius had done. The composition of a substance alone was sufficient to tell him whether it belonged to the class of salts or not. Salts were produced by the combination of acids of every kind with the most various bases, and in addition to neutral salts, he drew a distinction between acid and basic ones. With views so lucid as these, Rouelle was far ahead of his contemporaries. Rouelle's Cours de Chimie, according to Uffer, exists only in manuscript. End of Section 8. Recording by Sandra Kinzer, Madison, Wisconsin.
Section 9 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, InterfaceAudio.com. The Science History of the Universe, Volume 4, edited by Francis Rolt Wheeler. Chemistry, Chapter 7. The Phlogistic Period Proper, Part 2. The last of the French chemists of renown to adhere to the phlogistic theory was Pierre-Joseph Macquer, who was born at Paris in 1718. He became a member of the French Academy at the age of 27. Excellent opportunity for work was afforded him by his position as professor at the Jardin des Plantes, and his methods of research were more like those of the present. He determined the solubility of various salts in alcohol, and used this as a means of separating them from one another. Some of his researches were on potassium arsenate and on the coloring matter of Berlin blue. The later he identified with phlogiston because it was destroyed on heating. He was the author of several textbooks, Elements de chimie théorique, 1749, and Elements de chimie pratique, 1751, which were highly thought of. But his chief work was his Dictionnaire de chimie, which appeared first in 1766. This was the first dictionary of chemistry, and it was enlarged 3 times and translated into English, German, Italian, and Danish. Macquer died in 1784. All his life he remained a phlogistonist, and did all that he could to reconcile the continually augmenting dissidences between theory and facts. He paid no attention to proportions by weight, for it was only in this way that he could maintain the phlogistic hypothesis. And even although it was proved to be erroneous and untenable several years before his death, he was still unable to relinquish it. During the 18th century, many distinguished chemists flourished in Great Britain and Sweden, all of whom were adherents to the phlogiston theory of Stahl, and this notwithstanding the fact that it was their investigations, particularly those of Black, Cavendish, Priestley, Scheele, and Bergman, which destroyed the foundations of this theory. Black was born near Bordeaux in 1728 and died in Edinburgh in 1799. His father, a wine merchant, was originally a native of Belfast, being descended from a Scotch family, which had been settled there for some time. Black's original thesis for his degree was entitled Experiments upon Magnesia alba, quicklime, and other alkaline substances. It was published in 1755 and was reprinted in 1777 and 1782. During the 10 years he was professor of medicine at the University of Glasgow, he began and made great progress with his well-known researches on the heat of fusion of ice and the heat of vaporization of water, or as he termed them, the latent heats of water and of steam. The carbonates of the alkaline earths were before Black's time regarded as simple substances, and it was also supposed that when limestone was burnt, firestuff was taken up, and that this went over into potashes or soda when these were causticized by means of lime. Black, on the other hand, showed by his investigations that when limestone, carbonate of lime, or magnesia alba, was calcined, something escaped which caused a loss of weight, and which was identical with Van Helmont's gas sylvester. This gas, which he termed fixed air on account of its being held bound by caustic alkalis, lime, etc., he proved to be also present in the mid-alkalis, and these latter became caustic when deprived of their carbonic acid by lime or magnesia. In this research, methods are met with which have the imprint of a new departure. That Black devoted great attention to the proportions by weight of the compounds which entered into the reaction is seen in all his investigations, and it is thus easy to understand how he gave up the phlogiston theory and concurred in the doctrine of Lavoisier when the correct explanation of combustion and similar processes became possible through the discovery of oxygen. Cavendish, the distinguished co-worker and fellow countryman of Black, was born at Nice in 1731, 2 years before Priestley. But notwithstanding his brilliant circumstances, he lived the life of a recluse, devoting himself entirely to the furtherance of his beloved science. He died in 1810. His most important work was the discovery of hydrogen, which he called inflammable air. This he distinguished from the fixed air of Black, concluding that this inflammable air was the unaltered phlogiston of the metals. He was the first to attempt to determine the specific gravity of the gases. He showed that lime carbonate was held in solution in water by dissolved fixed air or carbonic acid. He proved in his experiments on air that when hydrogen was burned, water was formed, thus really determining the composition of water, though he did not recognize this fact. This led to a sharp controversy as to the phlogistication of the air of the atmosphere, and in the hands of the great interpreter of results, Lavoisier, did much to clear up and advance chemical theory. The opposition of Cavendish to the anti-phlogistic doctrine, which he helped to found by his own investigations, can only be explained by the fact that he did not take the proportions by weight in the processes of combustion into due consideration. The opposition of Cavendish to the anti-phlogistic doctrine, which he helped to found by his own investigations, can only be explained by the fact that he did not take the proportions by weight in the processes of combustion into due consideration, but interpreted the latter in a manner which appeared to him sufficiently convincing, viz. By regarding hydrogen, inflammable air, as identical with phlogiston. In addition to this, Cavendish showed a wonderful exactitude in his researches upon gases, whose specific gravities and volume ratios in chemical reactions he established. With what ingenuity he thought out and carried through physical experiments is well illustrated in his work on the specific heats of metal, and in his attempt, the first one which was successful, to determine the specific gravity of the earth. Another instance will be fresh in the memory of most readers, viz. Cavendish's suspicion, from the results of his own experiments on the combination of oxygen and nitrogen, that there was possibly still another gas present in the air, in small quantity, argon. When this marvelous versatility is considered, and the thorough mathematical training that Cavendish had gone through is remembered, the wonder seems great that he had too little stress upon proportions by weight in chemical reactions. Joseph Priestley was born at Fieldheads, near Leeds, in 1733, and received his education at a public school and at an academy of the dissenters. His studies were theological in character, and he became a dissenting minister. He was not a success in this work, becoming extremely unpopular even with his own sect. He also conducted a school, but was in very needy circumstances. He was able, however, to buy a few books and some instruments, including a small air pump, an electrical machine, etc., and was tireless in his work, training himself and his scholars in natural science. Meeting Franklin in London, he was attracted to the study of electricity and wrote a history of electricity. This, together with some new experiments on electricity performed by him, won some outside reputation and his election as Fellow of the Royal Society. He moved to Leeds, settling near a brewery. This gave him opportunity for examining the fixed air discovered by Black, which had been shown to be one of the products of fermentation. He collected this gas from the vats and performed many experiments with it. Moving away from the brewery, he had to prepare the fixed air for himself, and this led to his devising the simple and useful pneumatic trough. In the heated times of the French Revolution, his church and dwelling house were mobbed and burned, his library and apparatus destroyed, and he himself escaped with difficulty to London, and finally took refuge in America, where he settled in Pennsylvania. In this country, he pursued his scientific experiments, discovering carbon monoxide. He died in retirement in the year 1804. One French historian, Henri Gautier, states in his Essai sur la histoire de la chimie that Priestley sought an asylum among the Indians, and eventually his entire family died by poison. Priestley was a brilliant investigator, performing many most striking experiments. He was, however, neither thorough nor very careful, and was lacking in the scientific acumen needed for the proper interpretation of his results. It was upon the gases that his most valuable work was done. His invention of the pneumatic trough enabling him not only to discover new gases, but to investigate the properties of many already partially known. He considered that more is owing to what we call chance than to any proper design or preconceived theory in this business, and shows how large a share this element of chance had in his discovery of the new gas, oxygen. His method of experimenting is well illustrated by his own account of his discovery of oxygen, 1774. Having procured a burning lens, I proceeded with great alacrity to examine by the help of it what kind of air a great variety of substances would yield, putting them into vessels filled with quicksilver, and kept inverted in a basin of the same. After a variety of other experiments, I endeavored to extract air from Mercurius calcinatus per se, and I presently found that, by means of this lens, air was expelled from it very readily. Having got about 3 or 4 times as much as the bulk of my materials, I admitted water to it, and found that it was not imbibed by it. But what surprised me more than I can well express was that a candle burned in this air with a remarkable vigorous flame. I was utterly at a loss how to account for it. His experiments showed him that this air had all the properties of common air, only in much greater perfection, and he called it dephlogisticated air, regarding it simply as very pure, ordinary air. In 1843, Cuvier endeavored to show that the French chemist Bayen preceded Priestley in the discovery of oxygen. Bayen, however, in reducing precipitate per se, noted only the metal and entirely disregarded the escaping gas. He seems to have looked upon all gases as easily changeable, one into the other, at least in the first period of his work. Many experiments were made by him on the action of the various gases known to him upon animals and plants. He would place a mouse in the jar of the gas and notice the effect upon its breathing and general life processes. Plants were grown in similar jars, and the results upon the growth noted. He showed that air which had become noxious through breathing or the burning of a candle could be restored to its original condition by growing a plant in it. This, he said, was due to the impregnation with phlogiston in the first case, and its removal in the second. It is very probable, he wrote, that the injury which is continually done to the atmosphere by the respiration of such a number of animals as breathe it, and the putrefaction of such vast masses, both of vegetable and animal substances exposed to it, is in part at least repaired by the vegetable creation. He was unable to explain how this was accomplished. He held that all combustible bodies contained hydrogen. This was, in his view, phlogiston. The metals contained it, and their calces, or oxides, were simply the metals deprived of hydrogen. Thus he showed that when iron oxide was heated in hydrogen gas, the hydrogen was absorbed and metallic iron formed. Rich iron slag or cinder was, in his opinion, iron with some hydrogen retained. To prove this, it was mixed with the carbonates of the alkaline earths and heated strongly. This gave him an inflammable gas, and all inflammable gases were hydrogen in a more or less impure condition, according to his belief. That water could be impregnated with carbon dioxide was found out by him, and its use in disease suggested. Nitrogen dioxide and carbon monoxide were discovered by him, but his greatest discovery was that of oxygen gas. He examined sulfur dioxide, hydrochloric acid, and ammonia in the gaseous form. These are only the most important of his discoveries. Inaccurate in his experiments, he was decidedly weak as a theorizer. He was a firm believer in the phlogiston theory, and endeavored to explain the various phenomena noted by him by means of it. The important works of Priestley are the following: directions for impregnating water with fixed air in order to communicate to the peculiar spirit and virtues of Pyrmont water, and other mineral waters of a similar nature, 1772. Philosophical empiricism and experiments and observations on different kinds of air, 1774 to 1779. Experiments and observations relating to various branches of natural philosophy, with a continuation of the observations on air, 1779 to 1786, and experiments on the generation of air from water, 1793. Coetaneously with the three last mentioned British chemists, two eminent investigators, Torbern Olof Bergman and Carl Wilhelm Scheele, were supporting the phlogistic theory in Sweden, but their brilliant discoveries and observations only served so deeply to undermine it that its dispensation was inevitable. Bergman had acquired such a wide knowledge of the natural science that he taught with eminent success as a professor of physics, mineralogy, and chemistry at Uppsala. He was born in the year 1735 and died at the early age of 49, undoubtedly from the effects of overwork upon a weak constitution. His chief services to chemistry, to which from 1767 he mainly devoted himself, were in the domain of analysis, which he treated systematically and enriched by valuable methods. Bergman's system of wet analysis first took form during an investigation of natural waters, but he later made it embrace the examination of minerals in general, fusing such of these as were insoluble in hydrochloric acid with carbonate of potash. Bergman laid great stress on the analytical value of the blowpipe, between whose inner and outer flame he discriminated, and he endeavored to extend the use of such reagents as soda, borax, and microcosmic salt, substances whose value had been demonstrated by the mineralogist Cronstedt. It is to Bergman's pupil, Gahn, that the introduction of cobalt solution as a reagent is owed, and the substitution of platinum wire for the gold or silver used hitherto. Up to this time, reduction of the metallic state had been regarded as a necessary precedent to the quantitative estimation of metals in combination. Bergman now introduced the revolutionary method of combining them in stable salts of known composition, and from the weight of these calculating the metallic content. Bergman's analyses were not very accurate, yet they enjoyed the widest popularity. On the other hand, his German contemporary, Carl Friedrich Wenzel, found little consideration, though his method was similar, and his results more fortunate. Meanwhile, the number of chemists who applied themselves to the quantitative side of phenomena was steadily increasing, an indication of the straits to which the phlogiston theory had been reduced. Yet at this 11th hour, Bergman set to work to determine the relative quantities of phlogiston in metals. Believing that metals could only dissolve after conversion into their calces, he ascertained those weights of various metals which precipitated the same weight of some other in solution, surrendering their phlogiston to its calx. These weights, to his mind, contained the same quantity of phlogiston. He knew well how to render his chemical experiences useful for the definition and classification of minerals, mineralogical chemistry, and chemical geology. The current views upon chemical affinity gained through him precision and clearness. The scientific character of chemistry was materially raised by such observations, and a general survey of chemical processes rendered much easier. His papers appeared originally in the Memoirs of the Academy of Stockholm and Uppsala. Later on, they were collected together and published in 6 volumes in 1779 to 1790, under the title Opuscula Physica et Chemica. This Latin edition was translated into English in 1784 to 1791. Carl Wilhelm Scheele was born in 1742 in Stralsund, the capital of Swedish Pomerania, where his father was a merchant and a burgess. He was the seventh of 11 children. After receiving his education, partly in a private school, partly in the public school, gymnasium, at Stralsund, he was apprenticed at the age of 14 to the apothecary Bauch in Gothenburg. In those days, an apothecary was in large measure a manufacturer, as well as a retailer of drugs. He had to prepare his medicines in a pure state from very impure materials, as well as to mix them in order to carry out prescriptions, and indeed he himself often, as sometimes happens still, ventured to prescribe in mild cases. Scheele's master taught him such methods, and in addition instructed him in the use of chemical symbols in vogue at that date. These he afterward freely employed in his manuscripts, and this renders them exceedingly difficult to decipher. Restricted almost entirely to several old textbooks, together with the fairly good chemical inventory of Bach's shop, Scheele, by constant experimenting, acquired such a knowledge of things chemical that by the time he went to Malmö in 1765, he had gained more experience than the majority of the chemists of the time, although he was yet only an apprentice. At Malmö and also in Stockholm, 1768 to 1770, and Uppsala, 1770 to 1775, he increased his knowledge of the most important branches of chemistry, without, however, becoming so well known at the time as he deserved. It was only when, as stated by Nordenskjöld, through Gahn, he came into close relation with Bergman, a connection which began in a misunderstanding and coolness, but which developed into a friendship, that Scheele continued to gain steadily in reputation. After taking over the pharmacy at Köping in 1775, he was able to devote himself more closely to scientific work, with still more brilliant results. The records of his researches followed one another rapidly in the Transactions of the Stockholm Academy, into which he had been received as studiosus pharmacae in 1775. In 1777, he published the results of his investigation on air, oxygen, combustion, and respiration at Uppsala and Leipzig in a volume entitled Chemische Abhandlung von der Luft und dem Feuer, a chemical essay on air and fire. After his early death at barely 44 years of age, his collected works were published in 2 volumes in German by S. F. Hermstadt, Berlin, 1793, under the title Samtliche Physik and Chemische Werk. The Latin edition by Schaeffer had appeared 4 years previous. Although the results of his principal investigations will be discussed further on, it is important to mention here that to Scheele is due the first knowledge of chlorine and of the individuality of manganese and baryta. He was an independent discoverer of oxygen, ammonia, and hydrochloric acid gas. He discovered also hydrofluoric, nitrosulfonic, molybdic, tungstic, and arsenic acids among the inorganic acids, and oxalic, citric, tartaric, malic, and mucic among the organic acids. He isolated glycerin and milk sugar, determined the nature of microcosmic salt, borax, and Prussian blue, and prepared hydrocyanic acid. He demonstrated that plumbago is nothing but carbon associated with more or less iron, and that the black powder left on solution of cast iron in mineral acids is essentially the same substance. He ascertained the chemical nature of sulfuretted hydrogen, discovered arsenuretted hydrogen, and the green arsenical pigment which is associated with his name. He found new processes for preparing gallic acid, either powder of algarath, phosphorus, calomel, and magnesia alba. His services to quantitative chemistry included the discovery of ferrous ammonium sulfate and of the methods still in use for the analytical separation of iron and manganese, and for the decomposition of mineral silicates by fusion with alkaline carbonates. The greatest work of the life of Scheele, however, was his memoir on air and fire, which appeared in 1777, and which, on account of its relations to the chemical theory of that time, attracted universal attention, and was translated into English, French, and German. The chief part of the experimental material for this work, as is proved by the correspondence and laboratory journals published in 1892 by Nordenskjöld, was collected partly in Malmö and Stockholm, that is, before the autumn of 1770, and partly during the earlier portion of his stay in Uppsala, that is, prior to 1773. These dates are important in view of Scheele's relations as a discoverer to Priestley and Lavoisier. A number of circumstances, and more especially the dilatoriness of the publisher Swederus, retarded the appearance of the book. From the letters to Gahn, it appears that the manuscript was sent to the printer toward the close of 1775, but nearly 2 years elapsed before the work was made public. Scheele, in several of his letters, laments over the delay. In August 1776, he wrote to Bergman, "I have thought for some time back, and I am now more than ever convinced, that the greater number of my laborious experiments on fire will be repeated, possibly in somewhat different manner, by others, and that their work will be published sooner than my own, which is concerned also with air. It will then be said that my experiments are taken, it may be in a slightly altered form, from their writings. I have to thank Swederus for all this." However, no imputation of plagiarism was ever brought against Scheele. The whole conduct of his life was proof indeed against even a suspicion of unfair dealing. He was exceedingly unselfish and veracious. To quote Thorpe, "With all Priestley's candor and sense of rectitude, he had Cavendish's indifference to fame and his contempt for notoriety." It can be hardly doubted, however, that had Scheele's work appeared in 1775, he himself would have occupied a still higher position in the estimation of his contemporaries, and that it would not have been left to posterity to assign him his true place in the history of scientific discovery. He further expresses the following appreciation. "It seems impossible to read this, or indeed any other of Scheele's memoirs, without being impressed by his extraordinary insight, which at times amounted almost to divination, and by the way in which he instinctively seizes on what is essential, and steers his way among the rocks and shoals of contradictory and conflicting observations. It is perhaps idle to speculate on the causes which prevented Scheele from recognizing the full significance of his work. It may be that from the lack of mathematical training, the quantitative aspects of chemistry had few attractions for him, but it is equally probable that the peculiar character of his inquiries may have been determined by the circumstances of his position, by his poverty, and by the want of the refined and costly apparatus needed for quantitative research. But surmises, as Scheele himself said, cannot determine anything with certainty. It must be admitted that he was wanting in the faculty of coordination, grasp of principle, and power of generalization that so strikingly characterized Lavoisier, and his greatest investigation, while it testifies to his genius as an experimentalist, reveals no less clearly his weakness as a theorist. But when every legitimate deduction has been made, Scheele's work, with all its shortcomings and limitations, stamps him as the greatest chemical discoverer of his age. His story constitutes, indeed, one of the most striking examples of what may be achieved by the diligent cultivation of a single natural gift. End of Section 9. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 10 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The Science History of the Universe, Volume 4, edited by Francis Rolt Wheeler, Chemistry, Chapter 8, Part 1, Development of Special Branches During the Phlogistic Period. Although the services of the chemists whose investigations did most toward building up the chemistry of gases have been referred to, yet the influence of this work in shaping chemistry was so great that discussion of pneumatic chemistry and its relations to the phlogistic theory in more detail is necessary. Boyle, ingenious though he was unable to fathom the mystery of atmospheric air. His views regarding it are succinctly stated by him in his Memoirs for a General History of the Air, and in the same work he sums up the views of the ancients. His words are, "The schools teach the air to be a warm and moist element, and consequently a simple and homogeneous body. Many modern philosophers have indeed justly given up this elementary purity in the air, yet few seem to think it a body so greatly compounded as it really appears to be. The atmosphere, they allow, is not absolutely pure, but with them it differs from true and simple air only as turbid water from clear. Our atmosphere, in my opinion, consists not wholly of purer ether, or subtle matter which is diffused through the universe, but in great number of numberless exhalations of the terraqueous globe, and the various materials that go to compose it, with perhaps some substantial emanations from the celestial bodies, make up together not a bare indeterminate feculency, but a confused aggregate of different effluvia." His researches, however, show a marked advance over those of Van Helmont in the mode in which he collected gases and worked with them. At the same time, neither he nor his contemporaries felt quite sure whether carbonic acid and hydrogen, whose characteristic properties he was acquainted with, differed materially from atmospheric air. In fact, the idea that gases were simply atmospheric air with various admixtures had become fixed in the minds of the chemists. The experimentalist Stephen Hales, for example, discovered gases and prepared them in a more or less pure state, but had no theory to guide him, and concluded that it was possessed of a chaotic nature, since he failed to recognize his gases as different kinds of matter, but regarded them all as modified air. Black's account of fixed air and its properties is the first example of a clear and logical series of experimental researches, where nothing was taken for granted, but everything was made the subject of careful quantitative measurement. It was not long since Hales had announced air to be a chaotic mixture of effluvia. Black showed that common air contains a small amount of fixed air, and that fixed air must be considered as a fluid differing in many of its properties from common air, especially in its being absorbed by quicklime and by alkalis. It must be remembered that at that time carbon was not recognized as an element, and hence, though Black knew that fixed air was a product of the combustion of charcoal, he did not attribute it to the union of carbon with oxygen. Black held that the change from chalk to lime consists only in the withdrawal of fixed air, and that he adduced in proof the changes in weight accompanying the change from chalk to lime and back again. A piece of perfect quicklime made from 2 drams of chalk, which weighed 1 dram and 8 grains, was reduced to a very fine powder and thrown into a filtrated mixture of 1 ounce of a fixed alkaline salt and 2 ounces of water. After a slight digestion, the powder, being well washed and dried, weighed 1 dram and 58 grains. It was similar in every trial to a fine powder of ordinary chalk. The changes referred to are: chalk heated equals lime plus fixed air, CaCO3 equals CaO plus CO2, lime plus fixed alkali equal chalk plus caustic alkali, CaO plus K2CO3, CaCO3 plus K2O. The methods of collecting gases had improved considerably since the time of Hales. Air was ascertained to be a fluid capable of measurement, which possessed weight, and which could be transferred from one vessel to another, just like all other fluids. The apparatus which Black, Priestley, Bergman, and Scheele employed, and those which were used at the present time, gradually developed themselves from that of Hales. Joseph Priestley was the first to describe the collection of gases over mercury, and by this means he succeeded in discovering gaseous ammonia, hydrochloric acid, silicon fluoride, and sulfurous acid, gases which had been overlooked so long as water was employed in the collecting vessels. As mentioned before, Scheele is now known to have anticipated Priestley in the isolation of some of these gases, as well as of nitric oxide and sulfuretted hydrogen, hydrogen sulfide. These investigations, along with the recognition of Cavendish that hydrogen is a peculiar gas, and the supplemental researches of Bergman and Black on carbonic acid, are to be emphasized as being particularly noteworthy, since they help to do away with many misconceptions and errors. The discovery of so many gaseous substances of such different character naturally roused the chemical world. The properties of each gas were carefully studied, and after Mayow's researches, and especially after the more exact determinations conducted by Cavendish, the density was taken as the criterion of one gas differing from another, and from atmospheric air. Due attention was also given to the greater or lesser absorption of gases by water, as a distinct test for some of them. Bergman, for instance, determined with fair accuracy the solubility of carbonic acid in water. However, the exact composition of gaseous bodies remained unknown during this period, great uncertainty prevailing even about the simplest of them, until Lavoisier had pronounced his opinion as to the elementary nature of oxygen and hydrogen. But this could not be otherwise, so long as phlogiston was believed to be present in most gases. Hydrogen was thought to be identical with phlogiston by many chemists soon after the middle of the 18th century, Cavendish and Richard Kirwan setting the precedent for this. Others looked upon coal as being rich in phlogiston, if not as the latter itself, and often confused opinions were expressed concerning the composition of carbonic acid, carbonic oxide, nitric oxide, sulfurous acid, sulfuretted hydrogen, and other gases, these opinions being made to conform with the views of the phlogistic doctrine prevalent at that time. Of greater importance than these views upon the constitution of the gases just named were the long unsettled questions: is atmospheric air a simple or a command body? And if the latter, what are its constituents or ingredients? These questions were solved experimentally by chemists belonging to the phlogistic era, more particularly by Scheele and Priestley, but it was left to Lavoisier to interpret their observations correctly. The first observation which assisted in overthrowing the old assumption of air being a simple substance was the deportment of an enclosed volume to a burning body and to metals heated in it. The alchemists had asserted that when a substance is burned in the air, it is separated or analyzed into things simpler than itself. The acute Boyle had said the process is not necessarily a simplification. It may be, and certainly sometimes is, the formation of something more complicated than the original substance, and when this happens, the process often consists in the fixation of the matter of fire by the burning substance. He was led by his investigations in this direction to the assumption that one ingredient of the atmosphere was necessary to respiration and combustion, and that the increase in weight during the calcination of metals was due to a ponderable fire stuff. He remarked that it will not be irrational to conjecture that multitudes of these fiery corpuscles, getting in at the pores of the glass, may associate themselves with the parts of the mixed body whereupon they work, and with them constitute new kinds of compound bodies, according as the shape, size, and other affections of the parts of the dissipated body happen to dispose them. I have been induced to think that the particles of an open fire working upon some bodies may really associate themselves therewith, and add to the quantity. Boyle, The Skeptical Chemist, 1661. He was unable to isolate this ingredient, however. Stahl paid no attention to the change in weight resulting from calcination, a position which was taken also by many later phlogistonists, who either regarded such a change as accidental or advanced crude explanations of it. Johannes Juncker, for example, pointed out that the metallic calces were denser than the metals, and consequently heavier. Decidedly an incorrect statement, as Boyle had already demonstrated in certain cases that the calces were specifically lighter than their corresponding metals. Equally ridiculous was the assumption that the phlogiston which escaped in calcination possessed a negative weight, and therefore that the end product was the heavier. In 1630, Jean Ray published a series of essays entitled Essays of Jean Ray, Doctor of Medicine, on the researches of the cause owing to which tin and lead increase in weight when they are calcined. Now I have made the preparations, nay, laid the foundations for my answer to the question of the Sieur Brun, which is that having placed 2 pounds 6 ounces of fine English tin in an iron vessel, and heated it strongly on an open furnace for the space of 6 hours, with continual agitation, and without adding anything to it, he recovered 2 pounds 13 ounces of a white calx, which filled him at first with amazement, and with a desire to know whence the 7 ounces of surplus had come. And to increase the difficulty, I say that it is necessary to inquire not only whence these 7 ounces have come, but besides them, what has replaced the loss of weight, which occurred necessarily from the increase of volume of the tin on its conversion into calx, and from the loss of the vapors and exhalations which were given off. To this question, then, I respond and sustain proudly, resting on the foundations already laid, that this increase in weight comes from the air, which in the vessel has been rendered denser, heavier, and in some measure adhesive, by the vehement and long-continued heat of the furnace, which air mixes with the calx, frequent agitation aiding, and becomes attached to its most minute particles, not otherwise than water makes heavier sand which you throw into it and agitate, by moistening it and adhering to the smallest of its grains. The manner in which Ray arrives at his answer is not by any direct experiments on calcination, but rather by experiments and the reference to experiments of a purely physical nature, such as the discussion of the causes, like change of volume, which can, and of those, like heat, which cannot, produce change of weight. Thus he lays a sound foundation for his method, which is one of elimination, showing that none of the causes to which it had been usual to ascribe the observed increase in weight could be considered legitimate, that it could not be due to the giving up of heat of negative gravity, nor to the absorption of fire matter of positive weight, not to an increase in density, not to the absorption of soot or of anything else from the materials of the containing vessels. And so none is left unchallenged of all the possible modes of explanation, save that of the fixation of the air. Consequently, his conclusion that calcination of a metal probably consists in the fixation of particles of air by the metal does not amount to a proof. Mayow assumed that a spiritus igno aeris brought about combustion. According to him, the substance that is being calcined lays hold of this particular constituent of the air, which, however, he failed to isolate. Nevertheless, he approached closely to the correct interpretation of the phenomena in question, the real solution of which was brought forth after oxygen and nitrogen had been prepared with success. Nitrogen was first isolated by Scheele, but Daniel Rutherford, who discovered it independently in 1772, preceded Scheele in publication. Rutherford removed the oxygen from ordinary air by combustibles such as charcoal, phosphorus, or a candle, and having got rid of the carbon dioxide, in those cases when it was formed, by alkali or lime, he obtained a residue, now known as nitrogen. His view of the nature of this gas, in the phlogistic language of the time, was that the burning bodies had given up some of their phlogistic material to the air, which was thus altered. Nitrogen was phlogisticated air, even the incombustible. Hydrogen, too, was phlogisticated air, but air produced by the union of pure phlogiston with atmospheric air. The step taken by Rutherford, under Black's guidance, was an advance, though not a great one, in the development of the theory of the true nature of air. It followed from Scheele's as well as Rutherford's observations that this new gas, which was a non-supporter of either respiration or combustion, must be one of the ingredients of atmospheric air. The other was discovered by Scheele and Priestley. It should be mentioned here that passages in the early works suggest the possibility of a much earlier acquaintance with oxygen gas. Hofer, in his Histoire de la Chimie, Volume 2, page 271, claims to discover traces of a knowledge of oxygen gas in the writings of Zosimus, a Greek writer on alchemy, who lived in the 3rd or 4th centuries. In a manuscript preserved in the National Library of Paris, entitled Zosimus the Panopolitan, on the sacred art of making gold and silver, this passage occurs. Take the soul of the copper, which is borne upon the water of mercury, and disengage an aeriform body, soma pneumaticon. Hofer states that we have indications of the production of a gaseous body by means of a red substance, the soul of copper, which floats on the surface of liquid mercury. If this substance is red oxide of mercury, the aeriform body must have been oxygen. Moreover, in Campbell's Hermippus Redivivus, or the Sage's Triumph over Old Age and the Grave, which was published in London in 1749, the following statement occurs. I could mention another preparation from the vital part of the air itself, which is a great secret among these philosophers, and is perhaps the white dove, so often mentioned in the writings of Philolaethes, of which thus much is certain, that when the air is once despoiled of this principle, it is no longer fit for animal respiration, and it was by a contrivance of this kind that the famous Cornelius Drebel made that liqueur, which supplied the place of air in the machine he contrived for carrying on a kind of submarine navigation. This medicine, which is, as I have said, extracted from the air, is whiter than the snow, colder than ice, and so volatile that if a quantity of nutmeg be exposed to the air, it is absorbed thereby in the space of a few seconds. As Bolton has remarked, this passage refers to, in an unmistakable manner, to the preparation of oxygen and its property supporting life. Drebel, 1572 to 1634, appears to have rowed in a boat under water in the Thames River for a distance of about 8 miles, and his employment of compressed oxygen gas, if it may be so interpreted, must have been about the beginning of the 17th century. Scheele prepared oxygen by heating black oxide of manganese with sulfuric or arsenic acid, and also from nitrates, and from the oxides of mercury and silver, and noted its characteristics very clearly. Priestley, who also observed the gas at about the same time, without, however, recognizing its peculiar nature, first isolated it for certain on August 1, 1774, by heating red oxide of mercury, and as he published his results earlier than Scheele, he has generally been regarded as the first discoverer of oxygen. Both observed that this gas was capable of supporting combustion and respiration in an intensified degree. Priestley named it dephlogisticated air, and Scheele at first air vitriolicus, later fire air, and also life air. The discovery of oxygen enabled both Scheele and Priestley to recognize air as being a mixture of two kinds of gas. Priestley calls nitrogen phlogisticated air, and Scheele terms it spent air. Priestley employed saltpeter gas, nitric oxide, as an absorbent for oxygen, while Scheele made use of phosphorus, hydrate of protoxide of iron, mixtures of iron and sulfur, and moist iron filings. Both made the important observation that upon burning a candle in an enclosed volume of air, exactly as much fixed air, carbon dioxide, was generated as oxygen had vanished. Notwithstanding all this, they did not arrive at the correct explanation of combustion, respiration, and calcination, whose analogy to one another they clearly saw. The breathing of animals and the burning of substances were supposed to load the atmosphere with phlogiston. Priestley spoke of the atmosphere as being constantly vitilated, rendered noxious, depraved, or corrupted by processes of respiration and combustion. He called those processes whereby the atmosphere is restored to its original condition, or depurated, as he said, dephlogisticating processes. As he had obtained his dephlogisticated air by heating the calx of mercury, Priestley was forced to suppose that the calcination of mercury in the air must be a more complex occurrence than merely the expulsion of phlogiston from the mercury. For if the process consisted only in the expulsion of phlogiston, how could heating what remained produce exceedingly pure, ordinary air? It seemed necessary to suppose that not only was phlogiston expelled from mercury during calcination, but that the mercury also imbibed some portion, and that the purest portion, of the surrounding air. Priestley did not, however, go so far as this. He was content to suppose that in some way, which he did not explain, the process of calcination resulted in the loss of phlogiston by the mercury, and the gain by the dephlogisticated mercury of the property of yielding exceedingly pure or dephlogisticated air when it was heated very strongly. Consequently, the path distinctly indicated by his own observations was left for another to tread. It was Lavoisier who was destined to do this, as he easily threw aside the trivial phlogistic misconceptions that he cherished at the commencement of his scientific career. The others, indeed, supported a contradictory explanation of combustion and analogous processes in order to remain loyal to the phlogistic doctrine. But that it was Priestley and Scheele who, by their exhaustive investigations on oxygen and the part which it played in the processes mentioned, furnished the experimental material for the correct interpretation of these, and not Lavoisier, is beyond all question. It remained for the latter, however, to give the correct explanation of combustion, calcination, and similar processes. Among the treatises on air which appeared during this period, other than those mentioned, were Bond's Meditations Physico-Chimicae de Aeris in Sublinaria Inflexio, 1685, Arbuthnot's An Essay Concerning the Effects of Air on Human Bodies, 1751, and Cavallo's A Treasure on the Nature and Properties of Air and Other Permanently Elastic Fluids, 1781. In order to appreciate the advances which the chemical ideas of the phlogistic period showed upon those of the periods already discussed, and to understand the connection which exists between the theoretical views of the phlogistonists and those of the chemists of the modern period, it is necessary to become acquainted with their views regarding elements, chemical compounds, and chemical affinity. Boyle's definition of an element, that it is any substance which cannot be further decomposed, was one of great significance for the whole of natural science. He also considered that the elements attainable by chemical investigation were not the ultimate constituents of matter. Nevertheless, his contemporaries and successors, failing to appreciate these views, exhibit a tendency to revert to the alchemistic elements, and even to those of Aristotle. For instance, Lefebvre, author of a treatise on theoretical chemistry, and Lemery classified earth and water with 3 elements of Basilius, Valentinus, and Paracelsus, while Becher held to those 3 under other names, the vitrifiable and the inflammable, and the mercurial earths, and added water to the list. According to Stahl's views, sulfur consists of a sulfuric acid and phlogiston, and a metal of its metallic calx, oxide, and phlogiston. Therefore, the phlogistonists assume that all products of calcination and combustion, acids and oxides, were elements, in which class of substances they also classed phlogiston itself. These erroneous assumptions kept back a knowledge of the true elements, and only after it was clearly demonstrated that instead of the escape of phlogiston, the absorption of oxygen must be allowed, and in place of the assimilation of phlogiston, the removal of oxygen, did that extraordinary genius Lavoisier bring light into the confusion which prevailed by his brilliant ideas and observations. A better understanding of the composition of substances was gained by analytical chemistry, which was gradually developed during this period. But although certain constituents of compounds could be identified and distinguished from one another, yet the proportions by weight in which substances combined were not considered, and consequently the real development of the term chemical compound was reserved for the period of quantitative chemistry. The chemists of the phlogistic period were forced to draw their conclusions concerning the composition of substances from analogy, notwithstanding which fact, however, several contributed materially to an insight into the nature of chemical compounds. Robert Boyle, for example, recognized the dissimilarity of such substances to elements, while he, Mayow, and Boerhaave stated that the characteristic properties of substances which combine chemically disappear after such combination, notwithstanding the fact that they are still present in the compound formed. Acids, salts, and oxides, calces, were, however, regarded as being of similar composition, and until it was recognized that salts were produced by the combination of acids with bases, an achievement of this period, the term salt was applied promiscuously. Stahl, for instance, applied the term to acids and alkalis, as well as to salts proper, and considered that salts were made up of an earth and water. In 1745, Rouet rendered a great service to the study of salts and the diffusion of knowledge respecting this class of compounds in his attractive lectures. He defined salts as the products of the union of acids with bases, and distinguished normal, acid, and basic salts, and showed their action on vegetable dyes. Yet he confounded many salts with acids, and could not throw off the old idea that the vitriols and other metallic salts consisted of metal and acid. Bergman demonstrated the falsity of this assumption when he proved that it is the metallic calces and not the metals themselves which combine with acids to form salts. After the time of Rouet, solubility in water and taste were no longer regarded as characteristics of salts, inasmuch as he classed several insoluble compounds among them. End of section 10. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 11 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The Science History of the Universe, Volume 4, edited by Francis Rolt Wheeler, Chemistry. Chapter 8. Special Branches in the Phlogistic Period, Part 2. Important work on chemical affinity was contributed during this period, notwithstanding the fact that the old assumption that those bodies have an affinity for one another, which have something in common, that affinity is governed by this, remained a mental fixture with speculative chemists even into the 18th century. The term affinitas, used by Albertus Magnus to express this idea, presuppose the similarity of substances which interact chemically. As is generally the case, another idea evolved itself and has lived until the present time, side by side with the first, to which it is exactly contradictory. This considers union as dependent upon contrast, on polar difference, on an effort to fill up a want. This contrary idea found a devoted exponent in Boerhaave, who maintained that it is unlike substances which show the greatest tendency to combine with each other. His influence secured the general adoption of his views by chemists. After the time of Glauber, and particularly after that of Boyle, much attention was paid to the process in which the forces of affinity show themselves. Cases of so-called simple elective affinity, attractio electiva simplex, a term which originated with Bergman, were interpreted correctly by both the chemist just named and also by Mayow. For instance, the expulsion of ammonia from salmiac by fixed alkali, by the assumption that the attraction of the latter for hydrochloric acid was greater than that of this acid for the ammonia, Flüchtiges Gonzalez. Observations of this kind on the expulsion or precipitation of bases or acids from salts by substances endowed with stronger powers of affinity soon caused chemists to solve the order in which analogous bodies were separated from their compounds by others. The observations on the precipitations of metals and on the expulsions of various acids from salts by means of sulfuric and nitric acids, among others, may have tended in an especial degree to make clear the different strengths of affinity in analogous bodies. Stahl, the founder of the phlogistic theory, contributed important work on affinity. He attempted, 1720, to classify the effects of affinity by arranging similar substances in a series in the order in which they expel one another from a compound. The following mechanical experiment may serve as an example. Dissolve silver in nitric acid. It will take up the silver and appear as a light liquor. Into the clear and transparent liquor, throw thin strips of copper foil. The nitric acid will dissolve these and will drop the silver in the form of a powder. Pour this clear green solution onto lead foil. It will be attacked, and the copper previously dissolved will be dropped. Pour off the clear solution and pour it onto zinc. It will dissolve the zinc and allow the previously dissolved lead to drop. Into this clear solution put chalk. It will be dissolved and the zinc dropped. Then to this solution add spirits of urine, which will combine with it, releasing the chalk. And finally drop in lye. The solution will take it up and allow the volatile salt to go. Geoffroy used such a classification as the basis of his Table of Affinities, Tables de Rapport, 1718, in an arrangement destined to become very popular. The principle was to arrange similar substances so that the one following was always expelled by the one preceding from combination with the one heading the list. When thus represented, Stahl's example just quoted becomes nitric acid, potash, ammonia, lime, zinc, lead, copper, silver. But yet another most important discovery concerning the action of affinity is due to Stahl. He recognized the fact that a reaction occurring at one temperature in one direction could be reversed at another temperature, that at ordinary temperatures calomel is decomposed by silver, while under the influence of heat, silver chloride is decomposed by mercury. Such reciprocal reactions led to the suggestion to prepare tables of affinity for medium and high temperatures, both for wet and dry, i.e. fusion, reactions. Bergman made the attempt in 1775 to work out this proposal of balms by investigating the mutual behavior of a very large number of compounds, with the result that the doctrine of chemical affinity was materially advanced, insofar as this was possible by such empirical work. Bergman's work on affinity was published in his Opuscula Physica et Chemica. His views may be summarized as follows. There is a sequence in the magnitude of the elective affinities of a series of substances toward one which with they all combine, and this is manifested by the fact that the one possessing the greater affinity expels from the combination the one possessing the lesser affinity. This order is constant under each of the two different conditions of interaction, in the moist and dry way respectively, but differs under these two distinct conditions. The substance of lesser affinity is completely expelled by that of greater affinity, subject, however, to the possibility that the mass of the expelling substance may have to be very much greater than that required for simply replacing the expelled substance in the combination. It is impossible to reverse such a reaction. The following abstract from the table of Bergman on affinity will indicate the principles upon which it was based. Sulfuric acid, wet way, baryta, potash and soda, ammonia, alumina, zinc oxide, iron oxide, lead oxide, copper oxide, mercury oxide, and silver oxide. The dry way, phlogiston, baryta, potash, soda, lime, magnesia, metallic oxides, ammonia, alumina. Potash, the wet way, sulfuric acid, nitric acid, hydrochloric acid, phosphoric acid, arsenic acid, acetic acid, boracic acid, sulfuric acid, carbonic acid. The dry way, phosphoric acid, boracic acid, arsenic acid, sulfuric acid, nitric acid, hydrochloric acid, acetic acid. In the table order from top to bottom gives the relative displacing power. Thus, in combination with sulfuric acid, where the action takes place in aqueous solutions, baryta is represented as displacing any of the substances placed below it, and so with potash, ammonia, etc. Where the dry substances are subjected to heat, the order is changed somewhat. It was recognized then that the strength of affinity varied with the temperature. This is the attractio electiva simplex of Bergman. He recognized also an attractio electiva duplex. Mackay made use of the term affinitas reciproca, where two bodies seem to have nearly the same strength of affinity for a third substance, one replacing the other under slightly changed conditions, a partial recognition of the fact that affinity is dependent upon other conditions besides temperature. This should have sufficed to show the unreliable character of the various tables offered, but chemists were slow to give them up. Nor did they value at its true worth the remarkable work of Berthollet in the next period, and his conclusion that the action of affinity was proportional to the masses of the interacting substances. This, properly understood, entirely did away with all such tables, for a body with lesser affinity could displace one of greater, provided it was present in a sufficiently greater mass. Among the chemists of this period who wrote treatises on the subject of affinity may be mentioned Limburg, 1761, Murer, 1762, Wenzel, 1777, Keir, 1778, Weiglib, 1780, Elliot, 1786, Guyton de Morveau, 1786, and Schmeider, 1799. The growth of applied chemistry during the phlogistic period is next to be recorded. This division of the science was especially assisted in its development by that indispensable branch, analytical chemistry, in which notable advances were made. Qualitative chemical analysis, which had its beginnings in the iatrochemical period, was developed by the investigations of Boyle, Hoffman, Marggraf, Scheele, and Bergman. The first named introduced the word analysis for those chemical reactions by which individual substances could be detected in the presence of one another, and considerably advanced the analytical examination of substances in the wet way. He employed reagents to distinguish the important classes of compounds, and the systematic use of plant juices as indicators for the detection of acids, bases, and neutral substances originated with him. For this purpose, he used the coloring matters in the juices of litmus, violets, and cornflowers. Among the other reagents he introduced may be mentioned solutions of calcium and silver salts for the recognition of sulfuric and hydrochloric acids, respectively, infusions of oak leaves or gall nuts for the detection of solutions of the salts of iron, and volatile alkaline salt for the recognition of copper salts. He recognized ammonia by the white cloud that resulted when it came in contact with fuming acids, such as hydrochloric or nitric acids. Hoffman busied himself in analytical chemistry, mainly with the investigation of mineral waters. He examined many samples and showed that they contained carbonic acid, iron, common salt, and salts of magnesia and lime. He furnished valuable information as to the methods of testing for these substances, and also indicated many characteristics of mineral waters. The Tabelle über einige 40 Mineralwasser was an important contribution by Carl A. Hoffman, 1789. Marggraf, besides proving that gypsum consisted of lime and sulfuric acid, and that the latter was also a constituent of heavy spar, made use of the different colorations which the salts of soda and potash impart to a flame as a means for their recognition, and employed a solution of prussiate of potash as a test for iron. Scheele made many valuable observations in analytical chemistry. He it was who perceived the difference between soluble and insoluble silicic acid, and effected the separation of iron and manganese by acetic acid, in addition to independently observing the flame colorations of salts of soda and potash, and explaining the difference between the inner and outer flames of the blowpipe, a piece of apparatus which was introduced into chemistry by Gahn, Cronstedt, and Bergman. The latter was indebted to Scheele for many observations, but was more systematic than his contemporary. He suggested the use of liver of sulfur and sugar of lead as reagents, of hydrochloric acid or carbonate of potash to open up ores, and of methods for the separation of salts and the estimation of precipitates. The tests he employed for the recognition of sulfuric, hydrosulfuric, carbonic, arsenious, and oxalic acids, and of lime, baryta, and copper are still in use. Bergman was, to quote von Meyer, probably the first to proceed on the principle that an element should not be itself isolated and estimated according to its own weight, but separated in the most convenient form as an insoluble precipitate, for example, lime earth as oxalate of lime, and sulfuric acid as sulfate of baryta, in the determination of the weights of metallic precipitates. This procedure, in conjunction with the endeavors of Marggraf, Homburg, Scheele, and Black, to take the proportions by weight into account, in other words, to determine the quantity of a substance or substances present in a solution, furnished important preparatory work for the quantitative investigations of the next period. In the analysis of gases, the most noteworthy work on the period was done by Cavendish, who made a determination of the amount of oxygen in the air by exploding with hydrogen. He found that the oxygen amounted on average to 20.85%, a result which is only 0.05% short of the mean as determined at the present day. It was learned that carbonic acid and oxygen could be estimated volumetrically by the use of absorptives. Caustic potash was used for the absorption of the former, and phosphorus for that of oxygen. Mainly owing to the efforts of such investigators as Boyle, Kunkel, Marggraf, and Duhamel de Monceau, technical chemistry made considerable progress during the phlogistic period. In metallurgy, correct explanation of many processes were brought out, although in general it may be said that the methods of extracting metals from their ores underwent little improvement. In the manufacture of iron and steel, however, some material changes were made as a result of the investigations of Bergman, Gahn, Rinman, and René Reaumur. The latter's work, L'art de convertir le fer forge en acier de l'art d'adoucir le fer fondu, ou de faire des ouvrages du fer fondu assez fin que de fer forge, published in Paris in 1722, brought the author a pension of 12,000 francs from the Duke of Orleans, because of the improvements it effected in the manufacture of cast iron and steel. An account of Reaumur's method of softening cast iron was also embodied in Horn's essays concerning iron and steel, a work of useful observations published in London in 1773. Duhamel improved the manufacture of brass, and Marggraf introduced a more satisfactory method of preparing zinc from calamine. A valuable treatise by Knückel on the ceramic art and glass-making appeared in 1689. This work was entitled Ars Vitraria Experimentalis, and contained Neri's Arte Vitraria, with additions by Kunkel and others. After the introduction of the importation of chinaware, many attempts were made to imitate this true porcelain. In this, Bottker, 1685 to 1719, made the first advance in 1709, although it is now known that a porcelain of soft paste was made at Florence as early as 1580. Bottker made a red ware, but eventually, by employing kaolin, he made a true porcelain at Meissen. The process of manufacture remained a secret, however, and it was not until it was solved at Sèvres in 1769 by the experimental work of Reaumur and other chemists that the manufacture spread. In England, porcelain appears to have been experimentally manufactured at Fulham by Dwight as early as 1671, but it was not produced in quantity until about 1730, when works were established at Bow. In this connection, Higgins' experiments and observations made with the view of improving the art of composing and applying calcareous cements, 1780, should be mentioned. This treatise contained the results of valuable experimental investigations on the induration and strength of cements. Two works of great aid to the dyer, Marquer's L'art de la teinture en soie, 1763, and Hellot's L'art de la teinture de laines et étoffes de laine, 1750 to 1786, in that they contained speculations upon the manner in which dyeing operations are carried out, appeared during this period. Stahl, Hellot, and Macquer divided dyes into two classes, viz. Those capable of being fixed on cloth without the aid of mordants, and those requiring the use of such agents, and in 1794, Bancroft distinguished these divisions as adjective and substantive dyes. Prussian blue was discovered by Deisbach in 1710. Sulfuric acid, the manufacture of which constitutes one of the most important branches of modern technical chemistry, owing to the great variety of purposes for which it is required, was first manufactured on a large scale by a quack physician of the name of Ward, about the middle of the 18th century. For this manufacture, he employed glass globes of about 40-50 gallons capacity. A small amount of water being poured into the globe, a stoneware pot was introduced, and on this a red-hot iron ladle was placed. A mixture of sulfur and saltpeter was then thrown into this ladle, and the vessel was closed. The vapors evolved were absorbed by the water, and sulfuric acid was obtained. Roebuck of Birmingham was the first to suggest the use of leaden chambers instead of glass globes. These leaden chambers were set up in Birmingham in 1746 and were worked intermittently. The continuous working of them is an achievement of the 19th century. The manufacture of fuming sulfuric acid was first carried out at Nordhausen in the Harz by heating roasted green vitriol, but was subsequently removed to Bohemia. Rouelle demonstrated that nitric acid could be concentrated by distillation with sulfuric acid. A number of improvements were made in the manufacture of this acid by Stahl and other chemists, but hydrochloric acid was not prepared in large quantities, as it was not employed technically. As early as 1670, an artist, Henry Schwanhard, prepared hydrofluoric acid for etching figures on glass, and it is probable that his preparation was the same as that known to some artists as a secret in 1721, and published by Weigand in 1725. The alkalis and their carbonates were obtained just as in ancient times, viz. From the ashes of plants, incrustations on the soil, and carbonized tartar. However, it was shown by Duhamel and other chemists that common salt could be converted first into sulfate of soda, and finally into carbonate of soda. A description of such a process is contained in the Description des divers procédés pour extraire le soude de sel marin, published by the Imprimerie du Comité du Salut Public in 1795. Duhamel also introduced suitable methods of preparing starch and soap, and improved the processes of manufacturing sal ammoniac and sugar. His L'Art de raffiner le sucre, 1764, was held in high esteem in this period. Margraaf's discovery of cane sugar in the juice of the red beet has been referred to. It only remains to say that it laid the foundation for the now enormous and important beet sugar industry. The knowledge of the chemical elements and compounds was enlarged to a remarkable degree in the phlogistic period, and the discoveries made and facts learned afterward became of great technical importance. 6 new elements, chlorine, phosphorus, manganese, cobalt, nickel, and platinum, were added to the ones already known. Phosphorus was obtained by Brand, a Hamburg alchemist, in 1669, by distilling the residue from evaporated urine. He called it cold fire, and in 1671, Johann Elschultz of Vienna gave it the same name as the Bologna stone, or phosphor, which was discovered about 1603. The discovery of phosphorus caused much excitement on account of its properties, but its preparation was kept secret, and it was only after many endeavors that Boyle and Kunkel discovered the method of obtaining it. The phosphorus described by Balduinus in 1675 is thought to have been dry calcium nitrate, while that discovered by Homburg in 1693 was oxychloride of calcium. Kunkel, in several treatises on phosphorus, gave an account of its discovery and contributed to a better knowledge of the element. The first account of metallic manganese was given in the De Metallis Dubuis of Jacob Winterl and J.G. Kame, which was published in Vienna in 1770. Gahn, however, is generally credited with its isolation, which he effected in 1774. Cobalt was discovered by Brandt in 1742, and the earliest full account of the metal is contained in Johann Gessner's Historia Cadmi Fossilis Metallicae, Siv Cobalti, which appeared the next year. Nickel was first prepared by Cronstedt in 1750. The observations of Arvidsson on this interesting metal were published in 1775. Platinum is first referred to in Don Antonio de Ulloa's Relation Historica del Viage a la America Meridional, 1748. William Watson, an English chemist, was the first to examine the platina de Pinto, found in the Spanish West Indies by explorers, and his observations along with Brownrigg's experiments on the metal, were published in the Philosophical Transactions of the London Royal Society in 1751. Watson's experiments were continued by Lewis in 1755, Macquer in 1758, and Marggraf in 1761. De Buffon asserted that platinum was an alloy of gold and iron, and von Mille considered that it contained these metals together with mercury. Its elementary nature was not established to the satisfaction of all until the next period. The knowledge of organic compounds was also considerably extended, and new fields for organic chemistry were opened up toward the close of the period. However, the real composition of all organic compounds was not ascertained until the time of Lavoisier. Boyle investigated dry distillation, and proved that the liquid obtained by the distillation of wood is not a simple body, but that it contains, besides proliginous acid, an indifferent body which may be separated by distillation over burnt coral. The crude wood spirit thereby procured he termed adiaphorous spirit. He also wrote on the production and rectification of alcohol, a subject of frequent investigation by the chemists who followed him. Spirit of wine was prepared fairly pure, and was used in analytical chemistry for the separation of various salts, but confused opinions were held with respect to its formation in spirituous fermentation processes. Attempts were made by Reaumur in 1733 and Mathurin-Brisson in 1768 to determine the amount of alcohol in aqueous solutions containing it from its specific gravity. An interesting treatise on wines, Über der Verschung der Wein, was written by Friedrich Kartheuser in 1779, Frobenius 1730, Hoffmann, Pott, and Tuan Baum 1757, and Cadet de Gassecourt 1775 investigated ether, spiritus vini vitriolatus, but until 1800 it was believed to contain sulfur. A mixture of ether with alcohol, known as Hoffmann's drops, and the compound ethers were used officinally. Scheele discovered, or first clearly distinguished, the important organic acids, showing that grapes contained one, tartaric acid, which differs from that found in lemons, citric acid, that another, malic acid, occurred in apples, and again a new one, oxalic acid, was detected in wood sorrel. The later he prepared by the oxidation of cane sugar with nitric acid, and found that it differed from the one obtained by treating milk sugar with nitric acid, mucic acid. He also discovered lactic acid in sour milk, uric acid in bladder stones, and prussic acid by decomposing yellow prussiate of potash with sulfuric acid, and improved the methods of preparing gallic and benzoic acids. He showed that the latter forms a lime salt freely soluble in cold water, and therefore may be readily obtained by boiling gum benzoin with milk of lime, concentrating the filtrate, and separating the acid by means of hydrochloric acid. On the other hand, he learned that malic, tartaric, and citric acids formed insoluble salts with lime or lead oxide, by the aid of which substances they might be separated from other bodies in the fruit. He prepared the acids by decomposing their lime or lead salts, thus obtained with sulfuric acid. Formic acid was discovered by Ray in 1760, and was further investigated by Arfvedson and Cern in 1777. Its resemblance to acetic acid, which was now prepared in a pure form, was soon observed, and this produced some confusion. Marggraf proved that they differed. Oils and fats were frequently investigated, and Scheele showed that they contained a common constituent, oeleusis, or the sweet principle of oils. This is now known as glycerin or glycerol. Scheele stated that I is related to sugar, not only because of its taste, but also on account of the fact that both substances yield oxalic acid in treatment with nitric acid. The importance of this discovery was not realized until a much later date. Considerable progress was made during this period in medical and pharmaceutical chemistry, and many new medicines came into vogue. Among these were carbonate of ammonia, sulfate of potash, magnesia alba, and sulfate of magnesia. Among the textbooks which appeared may be mentioned the following: the Manductio ad Chemiam Pharmaceutium of Ravinus, 1690, Fix Chemicorum in Pharmacopoeia et Londinense Explicatio, 1711, von Ludolf's Die in der Medizinsche Chemie, 1750, and Baum's Elements de Pharmacie Théorique et Pratique, 1762. The advances made in organic and medical chemistry prepared the ground for the physiological chemistry, a branch which has been greatly developed in the most recent period. End of Section 11. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. Section 12 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio. InterfaceAudio.com. The Science History of the Universe, Volume 4, edited by Francis Rolt Wheeler. Chemistry, Chapter 9, Lavoisier and Antiphlogisticism, Part 1. Chapter 9, Lavoisier and the Antiphlogistic Chemistry. It has been seen how far the development of chemical knowledge during the 17th century was influenced by Stahl's phlogistic theory, that this theory exerted a decided influence on the progress of chemistry, but that it was too elastic to give exact definition to the tendency of investigation. It had, however, done good work, since it coordinated facts and developed unity of purpose, and served admirably as a period of preparation for the scientific experimental work of the era commencing with the discovery of oxygen by Scheele and Priestley, the modern chemical period. For 20 years following this discovery, a contest concerned mainly with the recognition of the experimental method was pursued. It had to do with the support of the method of observation under definite conditions as the foundation of all theoretic inferences and views, and with the subduction of the prejudices which had resulted from following the method which fostered speculation and the adaptation of observations, as far as possible, to the established system. This short period of revolution, 1774 to 1794, is rendered radiant by the reforms of one of the most remarkable men in the history of science, Lavoisier, who abolished old prejudices and masterfully applied scientific principles to the explanation of chemical phenomena. His combustion theory supplanted the doctrine of phlogiston, a change, it is true, that primarily only required the substitution of the words addition of oxygen for withdrawal of phlogiston, but which eventually resulted in a complete transformation of all ideas concerning combustion, calcination, and respiration, and consequently the views respecting chemical composition, a displacement which culminated in the conversion of the chemistry dominated by the dogma of Stahl into the anti-phlogistic system, the new chemistry. The phlogistic theory was deposed by the theory of oxygen, but as Whewell has pointed out, this circumstance must not lead us to overlook the really sound and permanent part of the opinions which the founders of the phlogistic theory taught. In this connection, we must not forget how much Lavoisier owed to his predecessors. He sifted and collated the facts handed down to him by the phlogistonists, and, mainly from the standpoint of the physicist, gave correct explanations of many processes. But he made no independent chemical discoveries, and is honored not as a Scheele or Black, but as the founder of a new system based on his comprehensive and correct explanations of the observations of other investigators. Consequently, it may be said that Gallic patriotic bias prompted Wurtz to state him in his Histoire des doctrines chimiques that le chimie est une science française, an assertion which was repeated 20 years later by Jagnot. Since, however, chemistry only took rank as a science when quantitative work was made its basis, Lavoisier must be given credit above all others in having directed it into and along this road. Antoine Laurent Lavoisier was born in Paris on the 26th of August, 1743. His father was wealthy and spared no expense on his education. In his 21st year, Lavoisier obtained a gold medal from the Academy of Sciences for an essay on the most appropriate method of lighting the streets of Paris, but it was some years before he made definite choice of his subject. He published memoirs relating to geology and to mathematics before the fame of Black's and Priestley's discoveries reached him and induced him to turn his attention to scientific chemistry. By good business management, he greatly added to his property and became a man of wealth. He lived well, giving dinners which were famed for their excellence and for the company gathered at them. This attracted attention to him and won for him some enemies whose influence was felt in the storm gathering against all that smacked of aristocracy. In addition, he was a fermier général, and though he brought about some reforms, some of his measures proposed to the government were exceedingly unpopular, as, for instance, his plan for taxing Paris. Impeached under the Reign of Terror, he was condemned to death and was executed, together with 28 other fermiers généraux, on the 8th of May, 1794. In Lavoisier is seen a mastermind, not only capable of devising and conducting experiments, but mainly of assimilating those of others and deducing from them their correct significance. Although his additions to the known chemical compounds were few in number, and cannot, as mentioned, be compared with those of Scheele or of Priestley, yet his reasoning in disproof of the phlogistic theory was so exact that it readily secured conviction, and laid the foundation for the new chemistry of the quantitative era. Hitherto exclusive importance had been attached to visible phenomena, but Lavoisier introduced a more exhaustive investigation of chemical reactions and the relations of quantity. The important work in which he recognized and explained the part played by oxygen in the process of combustion, calcination, and respiration embodies the chief investigations of his life, however, and in this lies his abiding service to science. The earlier observations of Rey, Mayow, and others, who had attributed the increase in weight of the metals during their calcination to an absorption of air, contained only the first germs of the true explanation of these processes. From the year 1772, Lavoisier engaged in investigations bearing upon this subject, the first results of which he delivered in a sealed note to the French Academy in November 1st of that year. This note was to the following effect. About 8 days ago I discovered that sulfur, when burned, instead of losing weight, gains weight. That is to say, from 1 pound of sulfur, much more than 1 pound of vitriolic acid is produced, not counting the moisture gained from the air. Phosphorus presents the same phenomenon. This increase in weight is due to a great quantity of air which becomes fixed during the combustion, and which combines with the vapors. This discovery, which I confirmed by experiments which I regard as decisive, led me to think that what was observed in the combustion of sulfur and phosphorus might likewise take place with respect to all the bodies which augment in weight by combustion and calcination. And I was persuaded that the gain of weight in calces of metals proceeded from the same cause. Experiment fully confirmed my conjectures. I effected the reduction of litharge in closed vessels of Hale's apparatus, and I observed at the moment of the passage of the calx into the metallic state, there was a disengagement of air in considerable quantity, and that this air formed a volume at least 1,000 times greater than that of the litharge employed. As this discovery appears to me to be one of the most interesting which has been made since the time of Stahl, I thought it expedient to secure myself the property by depositing the present note in the hands of the Secretary of the Academy, to remain secret till the period when I shall publish my experiments. Lavoisier. He was, however, in the same position as Mayow had been, that is, still in doubt as to which portion of the air caused this increase in weight, as to the air itself being a mixture of gases, and especially as to the nature of the process which occurred in the reduction of the litharge. He felt inclined to regard the generated gas, carbonic acid, as the fluid originally combined with the lead. This uncertainty was brought about by his giving little attention to the qualitative side of the chemical reactions. In 1774, after repeating these and similar investigations, Lavoisier found his error with regard to the reduction of litharge, and furnished more elaborate details of his observations, especially of the calcination of tin. He began by considering the possible solutions of the problem, and then investigated what changes really do occur, from which he inferred the cause. To quote from his Ouvres, "Thus, when did I at the beginning reason with myself, if the increase in the weight of metals calcined in closed vessels is due, as Boyle had thought, to the addition of the matter of the flame and the fire which penetrate the pores of the glass and combine with the metals, then it follows that on introducing a known weight of metal into a glass vessel and sealing this hermetically, determining the weight exactly, then proceeding to calcination by a charcoal fire, just as Boyle had done, and then finally, after calcination, before opening it, again weighing the same vessel. This weight must be found augmented by that of the whole quantity of fire matter which had been introduced during calcination. But if, said I to myself, the increase in the weight of the metal calx is not due to the addition of fire matter, nor of any other extraneous matter, but to the fixation of a portion of the air contained in the vessel, the whole vessel, after calcination, must be no heavier than before, and must merely be partially void of air, and the increase in the weight of the vessel will not occur until after the air required has entered. To test these theoretical considerations, Lavoisier selected the calcination of lead and of tin in sealed retorts. From 2 careful experiments with 8 ounces of tin, similar ones with lead were unsuccessful. Lavoisier found that the increase in weight of the tin on calcination was practically identical with the weight of the air, which took the place of that absorbed during calcination. His conclusions were as follows. Summing up the results of the 2 experiments on tin just described, it seems to me impossible not to draw the following conclusions. First, in a given volume of air, only a fixed quantity of tin can be calcined. Secondly, the quantity is greater in a large retort than in a small one. Thirdly, the hermetically sealed retorts, weighed before and after the calcination of the tin contained in them, showed no difference of weight, which evidently proves that the increase in weight of the metals arises neither from the fire matter nor from any other matter extraneous to the vessel. Fourthly, in all calcinations of the tin, the increase in the weight of the metal is sufficiently nearly equal to the weight of the air absorbed, to prove that the portion of the air which combines with metal during calcination is of specific gravity, approximately equal to that of atmospheric air. Thus, the problem he had undertaken had been solved by Lavoisier. He had ascertained the cause of the increase in the weight of metals on calcination, and had found it to be combination with a certain portion of the air. and having proved before that sulfur and phosphorus, on burning, also increase in weight and absorb a large volume of air, Lavoisier must, at that stage, as Freund remarks, be supposed to have established that combustion consists in combination with a portion of the atmospheric air, whereby the increase in weight on combustion is accounted for. However, he knew nothing as yet concerning the nature of the portion of the air absorbed. In the time between the memoir on the calcination of tin and his next contribution to the subject of combustion, falls Priestley's discovery of a gas obtainable by the heating of red oxide of mercury, the investigation of the properties of this gas, and the recognition that it is a better supporter of combustion than ordinary air. Lavoisier learned of this new fact, and his next paper bears evidence of the manner in which he was helped thereby. This paper, which was written in 1775, was entitled On the Nature of the Principle which Combines with Metals During Their Calcination, and which Increases Their Weight. In this he describes experiments showing that when metallic calces are converted into metals by heating with charcoal, a quantity of fixed air is expelled, and here for the first time he pointed out that fixed air is a compound of carbon with the elastic fluid contained in the calx. He then described the preparation of oxygen by Priestley's process of heating red oxide of mercury, mercurius precipitatus per se, and showed that the red oxide, when heated with charcoal, exhibited the properties of a true calx, inasmuch as metallic mercury was formed and a large quantity of fixed air was produced. In 1776, Lavoisier observed that the combustion product of the diamond was composed of carbonic acid alone, and in his next paper, which appeared the following year, he dealt with the combustion of phosphorus. He recapitulated Rutherford's experiments and showed that 1/5 of the air disappeared, and that the residue, to which he gave the name mouffet atmosphérique, is incapable of supporting combustion. As mentioned, Rutherford named this residue phlogisticated air, since he imagined it to have absorbed phlogiston from the burning phosphorus. Scheele, too, had made a similar experiment with a like result. From these observations, Lavoisier concluded that air consists of a mixture or compound of two gases, one capable of absorption by burning bodies, the other incapable of supporting combustion. The results of these investigations, along with the observations of Scheele and Priestley, and a research on the combustion of organic substances made in 1777, the products of which he showed to be water and carbonic acid, enabled Lavoisier to enunciate his views on combustion in a memoir published in 1778. The main points of this combustion or oxidation theory are as follows. Substances burn only in pure air, air eminent pure. 2. This air is consumed in the combustion, and the increase in weight of the substance burnt is equivalent to the decrease in weight of the air. 3. The combustible body, as a rule, converted into an acid by its combination with the pure air, but the metals, on the other hand, into metallic calces. Hence, the mechanism of combustion, according to Lavoisier, is represented by metal plus oxygen equals metal calx. Metal calx minus oxygen equal metal. Carbon withdraws oxygen, forming fixed air. In direct contradiction to the phlogistic scheme, metal minus phlogiston equals metal calx. In 1783, there appeared a memoir by Lavoisier entitled Reflections Concerning Phlogiston. After explaining the phenomena of combustion and reduction as a combination with oxygen or its separation, he proclaimed the non-existence of phlogiston, saying in part as follows, "But if in chemistry everything can be satisfactorily explained without the aid of phlogiston, it thereby becomes eminently probable that such a principle does not exist, that it is a hypothetical being, a gratuitous assumption, and sound logic is opposed to unnecessary complication. Perhaps I might have confined myself to these negative proofs and remained content to show that the phenomena can be better explained without phlogiston than by means of it. But the time has come when I must speak out in a more definite and formal manner concerning a view which I consider an error fatal to chemistry, and which appears to me to have considerably retarded progress by the method of false reasoning it has engendered. All these reflections prove that I have advanced what has been my object to demonstrate, what I will repeat once more, namely, that chemists have turned phlogiston into a vague principle, one not rigorously defined, and which consequently adapts itself to all the explanations for which it may be required. Sometimes this principle has weight, and sometimes it has not. Sometimes it is free fire, and sometimes it is fire combined with the earthly element. Sometimes it passes through the pores of vessels. Sometimes these are impervious to it. It explains both causticity and non-causticity, transparency and opacity, colors and their absence. It is a veritable Proteus, changing in forms at each instant. It was in this year that his important memoir upon the composition of water appeared, and it was this research which removed the last obstacles which the anti-phlogistic system had to contend. James Watt, the Scotch inventor, was the first to state distinctly that water is not an element, but that it is composed weight for weight of two other substances, one of which he considered to be phlogiston, and the other dephlogisticated air. And John Waltire, a friend of Priestley, was one of the first chemists to note that the deposit of moisture on the inside of a tube after exploding a mixture of air and inflammable gas. To Cavendish, however, belongs the credit of having first supplied the correct experimental basis upon which accurate knowledge alone could be founded. When Lavoisier learned that Cavendish had proved that water alone is produced by the combustion of hydrogen, information which was imparted to him by Sir Charles Blagden in 1782, he immediately repeated Cavendish's experiments on a large scale, and was assisted on that occasion by Laplace, Blagden also being present. A large quantity of water was produced, and the volumes of the combining gases were found to be 1 of oxygen to 1.91 of hydrogen. Not long after, in conjunction with Meunier, he performed the converse operation in decomposing steam by conducting it over iron wire heated to redness in a porcelain tube. The iron removed the oxygen from the water, while the hydrogen passed on and was collected in the gas holder. The explanation of the solution of metals in acids was now simple. It depended on the decomposition of water. While the oxygen combined with the metal to form a calx, the hydrogen was evolved. The calx dissolved in the acid, forming a salt in the metal. The operation of producing hydrogen by the action of steam on red-hot iron met with an equally easy explanation. The oxygen and iron united to form an oxide, the ancient Ethiops martial, while the hydrogen escaped. The converse occurred during the reduction of a calx to the metallic state by hydrogen. In this case, the hydrogen seized on the oxygen of the calx, removed it in the form of water, and the metal was left. These experiments were due to Cavendish. All that Lavoisier did was to indicate and prove the true nature of the phenomena. The opponents of the new doctrines, Priestley prime among them, exerted themselves to disprove the view that water was a compound of oxygen and hydrogen. But their efforts were in vain. Many of Lavoisier's opponents had to admit the justice of his views, and chemists of standing commenced the application of his ideas. First in France, Berthollet, 1786, de Marveaux, and the cautious Fourcroy, not until 1787, and soon in other countries also. Kirwan, for example, in 1792. Lavoisier's critical treatises, which were directed to showing the untenability of the phlogistic theory, conjoined with his Traité de chimie, gave the final blow to that doctrine. The new doctrine was accepted by the most prominent chemists after the comparatively short time which was required to put it to the proof. From the year 1792, after Klaproth, followed Hermstat, Gertner, etc. in Germany, Kirwan and Higgins in England, Troostwyk, Diemen and Van Merem in Holland, and Gilbert, Bugnatelli, etc. in Italy, had signified their adhesion to it. One may speak of the final victory of Lavoisier's system, and this notwithstanding the fact that still many chemists of great eminence refused to accept it in its full extent. For example, de la Mettrie, Sage, and Baume in France, Westrom, Gran, Kral, and Weiglub in Germany, Gadelin and Retzius in Switzerland, and Cavendish and Priestley in England. Some opponents of the new system, mainly owing to their misinterpretation of the Lavoisierian views, continued to combat it till about 1800. As late as 1796, Lamarck, for example, wrote an attack on the Lavoisierian theory of combustion, in which he referred to the pretended existence of a material called oxygen, which the pneumatic chemists have never seen nor studied, and the existence of which they imagined to explain the effects of fixed acidific air. A few words should be said in this connection with regard to Lavoisier's views on the relation of plants and animals to the atmosphere. Priestley already knew that oxygen was necessary for respiration, but his unfamiliarity with accurate analytical work and his close adherence to the phlogiston theory prevented him from arriving at a true explanation of the facts he observed. Lavoisier showed how oxygen was used up in the lungs in the formation of carbonic acid and of water, and how this process, which he properly classed as one of combustion, furnishes to man the heat necessary for his existence. He demonstrated that the expired carbonic acid derives its carbon from the blood itself, that in the process of respiration we thus, to a certain extent, burn ourselves, and would consume ourselves if we did not replace, by means of our food, that which we have burned. The experiments which Lavoisier made on respiration show the clearness of his methods. End of Section 12. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. Section 13 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The Science History of the Universe, Volume 4. Edited by Francis Rolt Wheeler. Chemistry, Chapter 9, Lavoisier and Anti-Phlogisticism, Part 2. One of Lavoisier's earlier memoirs that presented to the Académie des Sciences in 1770, entitled On the Nature of Water and on the experiments adduced in proof of the possibility of its change into earth, illustrates his accuracy, thoroughness, and acute reasoning. He states that the purpose of the research was as follows. I find myself confronted with the task of settling by decisive experiments a question of interest in physics, namely whether water can be changed into earth, as was thought by the old philosophers, and is still thought by some chemists of the day. It had been noted by many earlier investigators that when water was boiled for a long time in a glass vessel, a mass of white residue was found in the vessel after evaporation. This was long regarded as a conclusive proof that water could be changed into earth. Lavoisier weighed his glass vessel. Then, after heating water therein for 100 days, found there was no change in the weight of the vessel and its contents. When he evaporated the water, he obtained a residue of earthy matter, which he found corresponded, within the range of experimental error, with the loss in weight of the empty vessel. He therefore concluded from his experiments that the greater part, possibly the whole, of the earth separated from rainwater by evaporation is due to the solution of the vessels in which it has been collected and evaporated. Scheele afterward showed that this earth, or residue, possessed the same composition as the glass, thereby confirming Lavoisier's work. The old alchemical idea of transmutation was thus shown to be false, and was finally dismissed from chemistry. Lavoisier established the important generalization that matter may be changed, but not destroyed nor created. The matter lost from the glass vessel was merely dissolved in the water. This is the principle of the indestructibility of matter, the fundamental principle of modern science. However, it must be realized that while from the commencement of his experimental life, Lavoisier was guided in all his reasoning by the recognition of the principle of the conservation of mass, yet it was only after he had found this view proved by his work on combustion that he enunciated it, 1785. To quote from his Ouvres, "Nothing is created, either in the operation of art or in those of nature, and it may be considered as a general principle that in every operation there exists an equal quantity of matter before and after the operation, that the quality and quantity of the constituents is the same, and that what happens is only changes, modifications. It is on this principle that is founded all the art of performing chemical experiments. In all such must be assumed a true equality or equation between the constituents of the substances examined, and those resulting from their analysis. The establishment of the law of conservation of mass has followed curious lines. As Freund observes, Lavoisier did not arrive at it strictly inductively, by generalization from a large number of cases in which the weights of the substances participating in a chemical reaction were compared with the weights of those resulting from it. The available data of chemical investigations did not supply him with the material for so doing. The belief growing among physicists of the imponderable nature of heat, together with the old view of the indestructibility of matter in general, must have supplied him with the basis for an assumption, from which he drew deductions that were verified by the result of experiment. Generally speaking, ever since his time, the scientific world has been content to regard the conservation of mass as an axiom. A number of Lavoisier's statements indicate that his views upon the nature of his matière de chaleur, matter of heat, approximate to the mechanical theory of heat. Thus he states that heat is the energy which results from the imperceptible movements of the molecules of a substance. It is the sum of the products of